gravitation and quantum theory to pure mathematics, algorithms and biological modeling. In support of computational research, IMSC operates high performance computing clusters starting from Kabru and Annapurna. Now we have Nanda Devi and the recently added Comet, which is a 300 teraflop systems that significantly enhances our ability to conduct large scale simulations and data analysis. Now a few words about the present condition of our campus. So as many of you have noticed, IMSC is undergoing a, IMSC is undergoing a major infrastructure overhaul. The main entrance, for example, of the academic building and key internal services like internet and network infrastructure is being restructured to modernize the campus and to better serve expanding research activities. And we truly regret that your visit coincides with this status of the campus and you are seeing this transition. However, another thing is that separately the city of Chennai is undergoing a significant transformation with the new metro rail lines being constructed across the city, and this has led to disruptions in travel and accessibility for many of you at different parts in Chennai. And we thank you for your patience, and we hope that in the next edition of Cosmic Connections you will return to see both revitalized IMSC and more connected Chennai. Now let me come to the meeting, this national meeting about Cosmic Connections. So unlike broader meetings like IAGRG, so why, here I'd like to explain why we needed this Cosmic Connections. So there are platforms like IAGRG or WEB which host talks on a wide spectrum of topics, but Cosmic Connections we designed to be focused mainly on cosmology from the earliest moments of the universe to the large scale structure. And the aim is to create dedicated annual platform for Indian cosmology community and bring together theorists, observer, even instrumentation experts under one roof. And this year's program spans early, intermediate and late universe and is meant to encourage interactions across the subfields and career stages. And it can be used as a platform for the next generation. We plan to make Cosmic Connection a stage for the early career researchers. That is why we offer nearly equal talk durations for students, postdocs and faculty, ensuring the young scientists to have an opportunity to showcase their work, engage with the community and explore the academic opportunities. And we have also maintained, as you have noticed, maintained a strict in-person format to foster genuine interaction and collaboration, which is not always available in virtual mode. And this inaugural edition is something that we are really proud of, and we hope to build on. And our vision is for Cosmic Connections to become an annual national meeting offering a focused, inclusive and high quality space for cosmology research in India. And now I'd like to take a few moments to show a few slides that will help you to know about the organizers in the conference. So these are the scientific members of the scientific organizing committee. So I'm happy to say that apart from one scientific organizer, we have everyone in this meeting. Not everyone today, but we already have Professor Susmita Adhikari from ISAT Pune here. We have Professor Prabhavati Chingambam from IIA here. Professor Ranjan Laha from IISc Bangalore here, and Professor Asim Paranjpe, we tried to bring him here, but because of the travel commitments he could not join. Professor Tirthankar Roy Chaudhary is already here from NCRA TIFR. Professor Tarun Sorodip is going to join tomorrow from RRI Bengaluru, and Professor Sriram Kumar is here, who is the first chair of the first session. And these are the local organizers whom you have interacted with already, and whom you can reach out to if you have any questions. So there are two local organizers from IMSC, from our institute, Debabrata Chandra and Dr. Samuel Lopez, who are here. And from IIT Madras, we have Alipriya Huri and Dr. Arnab Pal, who are sitting there. Now, registration, as I have mentioned in my email yesterday, that registration will be done today only and at the desk. But if you have missed your registration, and if you come tomorrow, somebody is coming tomorrow and they're listening to us here now in online mode, I would like to request that please reach out to the local organizers around the coffee breaks at 11 and 1600 hours. And please keep the badges with you. There are no lunch or dinner coupons. We keep things very informal here, but having the badges will still be helpful. Wi-Fi ID and password, these are provided during registration. This should work with IMSC Wi-Fi and IMSC Wi-Fi testing. Both should work. And if you do not have, please collect it from the LOC. This is a very important point that please, I would like to request you to submit your download links for your talks in the email that I sent to you on July 22nd. Please avoid bringing your slides on pen drive just before the session. Let's use the coffee time to enjoy coffee, and let's have it for all. And please inform the local organizers if you plan to use your personal device, and the local organizers will get in touch with you and then they will get in touch with the media team, and they'll make sure that it happens. We have already tested some Mac device today morning. However, if you are delivering the talks from your own device, we will still need your talks because we plan to upload it in our website. Some of you have indicated that you do not wish to be recorded and streamed. So we have already communicated to the media team that in such cases your streaming will be paused and the recording will also be paused. We will not put anything in the media. However, we kindly ask you to reconsider. In that case, please, if you reconsider and think of allowing permission to record your talks, just write to one of the local organizers with a CC to me so that we can record seamlessly and without interruption. And this is important because many researchers are actually listening to this conference online. Now, if you are speaking in a 20-minute talk slots, the SOC kindly requests you that you include a brief 1 to 2 minute overview of your subject at the beginning, and please respect the time limit as we have only 5-minute buffer between talks, and participants are requested to ask the questions after the talk, but it is entirely up to the session chair how the session chair is going to conduct the session. Transportation. I have already sent the emails, but if there are accommodation changes, etc., I would like to tell you again. Buses will depart from IIT Madras Ginger at 8 a.m. in the morning. Buses will depart from Pallavaram at 7:30 in the morning, and the return buses will leave from IMSC at 9:30 p.m. after dinner. And if you are not staying at IIT Ginger or at Pallavaram, there are some participants there, but wishes to avail the bus services, please let me know because we need to communicate that to the driver. The office is going to do that for you. So that was about transportation. Poster boards, I have seen that they are already set up outside, and you can pin the posters. I think we already have the pins for you. If not, by tomorrow we will have, and you can put it outside. It is in front of the library. It is in the library portico, and you can do that during the coffee breaks. Now, regarding meals, we have organized the meals based on your dietary preferences that you had indicated in the registration form. Except for the conference dinner and the special dinner on the outreach day that are happening on July 30th and July 31st, all other meals will be served outside Ramanujan Auditorium here, as you have had today your breakfast. And the conference and special dinners will take place at the Institute of Hotel Management. So it is just 100 meters from here, okay, on the same side of the road. So we will lead you there during the event, and you can just follow any of the local organizers to reach IHM. And since we have received an overwhelming number of registrations, and we could not accommodate all the participants, and we are really sorry for that because of the limited resources. But it is important that those applicants get a chance to follow this meeting. So that is why we are having this meeting live streamed, and at the same time we are recording and we will keep the sessions recorded. Each session will be kept separately after a few days after our media team edits all the sessions. So it will be live streamed via YouTube. This is the channel, Math Science channel. So in order to allow everyone to follow, please spread the word, and if you want to do it in Twitter, this is our Twitter handle. One caution you should take, that mention the meeting as Cosmic Connections. Try to keep the, remember to put the S in the end, not Cosmic Connection, because it is an name of the Astrology Institute, and we really do not want to give a mixed signal. So apart from that, I think we are done. That's it, and let's start the conference. Professor Sriram Kumar is going to chair the session. So we still have 3-4 minutes. Please take over, Sri.
Just wait for a couple of more minutes, so that people online will also be waiting for us to start at 9:30. The slides are in place.
Yes,
slides are put on. The slides, please.
It's on? It's on?
Yes. Yes.
He is going to do that.
First two speakers. What? Harsh? Purushottam. Navik Bhattacharya. 17 plus 3. நம்ம ஆரம்பிச்சிடலாம்ப்பா. முதல் 2 டாக் சரியா இருந்தது. Pointer manner. Good morning, everyone. Welcome to the first day, first session of Cosmic Connections. We have 5 speakers in the session. Our first speaker is Rishi Khatri from TFR Mumbai. He will be speaking about understanding the universe with the cosmic microwave background. We would request you, as Dheeraj mentioned, to keep the questions at the end of each talk. Over to you, Rishi.
Okay. Thanks, Sriram. So I want to talk about few different aspects of the CMB, starting with something more familiar, the anisotropies or the primary anisotropies of CMB, and CMB spectral distortions also, which are the deviations of the CMB from a black body. But also now with future experiments which are geared towards polarization and with many different channels, it has become possible to also dig out many new signals, higher order signals from the CMB, which have more information about not just early universe but also about the late time universe. So hopefully I will have time to talk about that also. So this background that you see is actually the familiar cosmic microwave background, primary anisotropies. I have just plotted it in a different way. Instead of a color map that you are used to seeing, I have plotted it in 3 dimensions. So the high temperature, this is a small patch of the sky, Planck 143 gigahertz map. So these peaks are where the temperature is slightly higher, few hundred microkelvin more than the mean, and the dips are where it is few hundred microkelvins less than the mean. And you see there are some very deep dips that like this one. So that is basically not the primary anisotropy, that is a secondary anisotropy. So this dip is where the CMB has passed through clusters of galaxies and the CMB photons have been upscattered. So at 143 gigahertz there is a deficit of photons. So you get a very deep negative temperature dips here. So this is the mechanism by which, for example, these telescopes which don't have many frequency channels like SPT, South Pole Telescope, they look for clusters. They look for these very deep dips which are deeper than the usual primary anisotropies. So let's start with a little bit of background. So this is again a picture of the universe. By definition, we are at the center of our own observable universe. As we look out further, we are also looking back in time. So the important epoch for CMB is about when the universe was about 380,000 years after the Big Bang, or redshift of around 1,000 or 1,100. So that is when, before this, the universe was a plasma. So the photons were not free. They were free electrons. All the electrons were free. So CMB photons were scattering. They could move, the mean free path of the photons was very small. So they would travel a little bit in a straight line, but then scatter off a electron into a random direction and so on. So they were doing a random walk in a sea of electrons, right? So what that means is that universe was opaque because photons could not travel very far. But at last scattering surface, the universe recombined. In particular, the protons and electrons recombined to form neutral hydrogen, and universe became from opaque to almost transparent. And after that, the photons are coming almost directly towards us. So that is why this is called last scattering surface, because this is approximately the surface where the photons that we are seeing today, they last scattered. Of course, this is not a very sharp surface. This is a it has some thickness, and for some photons scatter again when the universe starts getting reionized again by the first stars around redshift of 10 or so, between redshift 10 or 6 mostly. But this is not all. So this CMB anisotropy, so the picture of the sky that we see in the CMB, we can only go as far as redshift of 1100. Right? Before that, the universe is opaque. So the CMB spectral distortions actually, it turns out, they allow us to look even beyond this opaque surface and look all the way up to redshift of around 2 million, when the universe was, if you say here, it is about 70 days old. So that is very exciting because it allows us, the CMB spectral distortions or the deviations of the CMB from a black body spectrum, it allows us to learn about the universe, what was happening, the dynamics of the universe that was happening between as far as redshift of 2 million. So let me start with first primary anisotropy. So I told you that universe is a plasma before the recombination. So in particular, the photons cannot travel very fast. So the photon-electron fluid along with protons are coupled to electrons and ions are coupled to electrons through Coulomb scattering. So they behave as a single fluid. So it is very interesting that this fluid has very interesting property. Nothing, no fluid like this exists today, right, or in the lab. In the lab we have plasma, relativistic plasmas, but that is also very different from this fluid. So the importance of this fluid is that the energy density is dominated by photons, relativistic particles, or almost. By the time of recombination, it is almost half-half or comparable energy density in baryons and photons. But the pressure is completely dominated by radiation pressure. So we can say that if you go even further, earlier times, then the energy density is also completely dominated by photons. All baryons are doing is they are providing a opacity to the fluid, so that photons cannot travel very far, so photons behave like a fluid. So the only job of both baryons is to make photons to behave like a fluid, but it is really a fluid of light. And the important aspect of this fluid is that there are sound waves in this. So there are small perturbations. The universe is almost completely homogeneous, but there were small perturbations initially. And if you have perturbations in a fluid, they will oscillate. In particular, they will oscillate as sound waves. So we have sound waves in a fluid of light. If you think about it, this is actually quite an interesting thing. Nothing like this we can make in lab or in the low redshift universe. And these sound waves, they are described by a very simple equation. This is the equation that you learn in your first year of classical mechanics. This is a forced damped oscillator equation, right? This is a simple harmonic oscillator equation. So we do a Fourier transform. So we look at each Fourier mode separately. And each Fourier mode behaves like a super harmonic oscillator. So if you take just the first term and the third term, this is just a free oscillator. So it will just oscillate with a particular frequency given by sound speed. And the wavelength that we are looking at, k is the wave number. There is a damping term. Damping is happening because these parameters of the oscillator are not fixed, but the universe is expanding, so the pressure is gradually decreasing, energy density is also decreasing. So that gives it a damping term. So it depends on the R is the ratio of baryon to photon energy density. So how much damping is happening, it depends on how much baryons there are, or the baryon baryon energy density. So you already see that we can, if you study the sound wave, we can get the omega matter baryon, omega baryon parameter out of it. But the most important thing is, the most important aspect of this is the forcing term. So forcing term is coming from gravity. Right? So the oscillator does not, the restoring force here is pressure. So even without gravity, you will have sound waves. We don't need gravity to have sound waves. But the forcing term, the gravity, what it does is it provides a forcing term to this oscillator. For example, if you have dark matter sitting there, then dark matter is providing a constant force. So in particular, so without the forcing term, we will have free oscillations, resonant. So if the forcing term, suppose there was no dark matter, there was only baryons, then baryons will actually act as a resonating forcing term. What that means is that if you increase the over density in the sound wave, where you have high over density, then the gravity will also higher, so it will make the baryons compress even more. Where you have under density, the sound waves have under density, it is going a rarefaction. The baryon density will also decrease, and it will the gravity will decrease, so baryons will move out even more. It will empty out even more than they would have without this forcing term. So the forcing term due to baryons is like a resonant term. So if there is no dark matter, the resonant term means that, as if you remember from classical mechanics, there is amplification of oscillations. The oscillations will actually, usually they will amplify quite a bit, but the damping term will stop the oscillations from just running away. But still you will have the amplitude of the oscillations will be much bigger if you had only baryons and photons, there was no dark matter. But the dark matter, because there is dark matter acts like it is just sitting there. If there is overdensity in the sound wave or underdensity, it does not care because it is uncoupled. The overdensity in dark matter remains overdensity, underdensity in dark matter remains underdensity. So it is like a constant forcing term. And if you give a constant forcing term to a simple harmonic oscillator, it just shifts the 0 point. And that gives you this asymmetry in odd and even peaks, because when you square the sound wave, so this is shown here, you have a sound wave, and if you square it, what you will get is so the sound wave, if you plot as a function of a mode, k mode, it will have odd even peaks, but we are interested in power spectrum, so we will square this. So without baryons, you will have all the peaks of the CMB acoustic oscillations, they will have the same height. But when you add dark matter, then you have a shift in the 0 point, and when you square this, you have this odd even asymmetry. So that tells you. So you can. So this depends the asymmetry and the amplitude. It is basically telling you how much baryons there are, how much dark matter there is. But we also have neutrinos in the standard model of cosmology, and neutrinos do something very interesting. They are not coupled with anything, but they are relativistic, unlike dark matter, which is non-relativistic. So if you have overdensity in dark neutrinos, initially we have adiabatic initial conditions, so all fluids have the same overdensity or underdensities. But if there is overdensity in neutrinos, it will not remain an overdensity because neutrinos are relativistic, they will just stream out of the overdensity. And the neutrinos from overdensity will mix in underdensities and underdensities with overdensities, so we already raise out those perturbations. In particular, the scale that you are erase the perturbation is the scale in which the neutrinos can travel in a hover time, which is basically the horizon size, right? So as soon as the neutrinos enter the horizon, the perturbations outside horizon, they have a constant perturbation. It is just sitting there just like dark matter, but as soon as they enter the horizon, the perturbation decays away at the speed of light, whereas sound speed is much slower than the speed of light. So which means this is forcing term due to neutrinos is like a step function. And if you apply a step function to a simple harmonic oscillator, again you can do calculate this analytically, it gives you a phase shift in the oscillations. So the peaks just move a little bit. And so we observe all this combined effect of all these effects during time of recombination. And in particular, this important aspect of this is that it also provides us with a standard ruler. So we are here, if you look at these oscillations, there is k, cs, eta, and in particular this distance between the peaks or the position of the peaks in the k space, it depends on the sound horizon, r star, and the distance from us to the CMB, which is this angular diameter distance. Right? So what we observe is the angular scale of these peaks, and it is given by r star, approximately r star over dA, and we actually do the spherical harmonic transform, so we will look at as actually the L modes, which are inverse of 1 over theta, which is dA. So the L modes at which you will peak depends on the ratio of dA to r star. And then we do the spherical projection. So these are 3 dimensions I was talking about, but we see that CMB in 2 dimensions. So that projection from 3 to 2D is determined by these Bessel functions. And in the end, you can do a little bit of mathematics, and you can write down the formula for the CMB power spectrum that we will see today. And in particular, the spherical Bessel functions projects the k modes where the peaks will happen to the L modes, which is given by this k times dA. Right, and the k is related to again the sound horizon. 5 minutes, okay. Right. So this is the picture we have already seen. So we observe the CMB peaks, we measure the parameters. I will just go a little bit faster. So the peak that we see is given by, if we combine everything, if we have dA over R square, but we also have to include there is a phase shift due to neutrinos. So it's an additional factor which comes here, right? And the angular diameter distance depends on the expansion history. It is the integral of Hubble from 0 to z star. Sound horizon is the integral from z star to infinity. And then there is this Hubble tension, the famous Hubble tension we know. So which means that if you measure L peak, then dF through dA and R star, we have the sensitivity to S0. So that is how you measure this Hubble constant. As for CMB, measurement is slightly lower than the direct measurement. So the question is, what is going on? It seems now with the recent papers, it is most likely a systematic. There have been some interesting papers on systematics which have been appearing on archives recently. But if you say that, okay, we want to keep these energy densities of matter and radiation fixed, because they determine the oscillator and we have a pretty good handle of how much there should be, and you want to boost the Hubble from CMB to solve the Hubble tension, then what you will find is that you just add a constant to the Hubble parameter all throughout the history. But as you go early times, the universe is expanding faster, so this constant addition is almost negligible. So all this does is it basically affects the dA, but does not affect the R star. So dA, if you boost the Hubble, then dA becomes slightly larger, R star remains unchanged, so the peaks shift to smaller L, and that will contradict the observations, right? Theoretically, you do this exercise, you find that you contradict the observations, so you have to do something to bring the observations back to, the theory back to the observations. So one way is to you change dA, so you manipulate the expansion history so that even after changing Hubble, dA remains same. Or you can change R star, that is the early solutions. You change R star to compensate for dA. But we what came up with, there is also this additional factor phi. You can actually use phi to compensate for dA. So you change this phi, the phase shift due to neutrinos, in such a way that it undoes the change in dA. And that was the, so you can calculate how much phase shift you need, and it turns out that if you stop the neutrinos from free streaming, so the Foregrounds transform is not a step function, but it is a constant, then actually it gets you the right answer. And in fact, so you can see that it's just showing that you boost the Hubble, this is the original lambda CDM dashed red line. You increase the Hubble, so the peak shift, but then you stop neutrinos from streaming, it comes back, it undoes the change. So if you start just, and again you can do Monte Carlo and do a little bit of more, so it's possible that we measure, if it is really new physics, then one solution is just that there is a new interaction of neutrinos which is stopping them from free streaming, and that is basically changing the phases. And so I have a few more minutes maybe. So let me just go to, very fast now I will go through the CMB spectrum. Spend a little bit more on Hubble tensions because I think this is the fashion in vogue right now. But let me show you what we can do in the future. So standard model already predicts spectral distortions at the level of 10 to the minus 8. And actually the SZ effect from clusters is already at a level of 10 to the minus 6 in the monopole. But if you don't look at the monopole, you look at the particular patches of the sky, we already direct the thermal SZ effect at the cluster, as I showed you in the first slide. So in the black body spectrum, it was measured many years ago by COBE satellite, and that is the only measurement that we have. After that, anisotropics, many experiments, but there is no experiment on spectral distortions. And as I told you earlier, that we can actually look all the way up to 2 times 10 to the 6. So in particular, if you have something exotic happening, for example, some dark matter decays or primordial black holes are evaporating, or you have some cosmic strings or topological defects which are injecting energy, high energy particles into the plasma, and these high energy particles will trigger a particle cascade, just like cosmic showers do in the atmosphere, or what happens in the colliders, where your particles collide and then you have a shower. So here you inject high energy particles and they will collide with the plasma and they cascade down in energy, and until at some point most of the energy ends up in boosting the CMB photons, because CMB has the most entropy, the entropy is dominated by CMB, so any energy you inject goes into a CMB. You can also have scenarios where instead of injecting energy, you absorb energy. For example, you have a dark matter, which is like a hydrogen atom or a nucleus. It has internal levels. It can actually absorb CMB photons. So we did this calculations. So before that, people were just looking at y and mu distortions, but if you calculate this more carefully, you find that the distortions have actually a very rich structure. You can have even double peak structures. These distortions are very different from y or mu distortions. So there is a lot of information in this shape of the CMB spectral distortions. In particular, the constraints that we put, for example, in decaying dark matter, they change quite a bit. So this is the gray line that people have been doing until now, assuming your energy goes into y or mu. But if you do it correctly, then you see that actually they can relax by a factor of 5. So there is a huge effect. So we recalculated all these constraints of different things. So you can do unstable particles or decaying dark matter, primordial black holes. So we updated all these constraints. We also have BBM. So these energy particles can destroy the elements producing BBM. That also gives you some constraints. So we calculated all these again. I told you about if a dark matter is, for example, a two-state thing, and you can absorb CMB. It turns out if you tune the parameters just right, you can actually explain the edges of anomaly. You can, I have not shown that here, but you can actually, it can actually give you the edges anomaly. So the signal that edges is saying it is coming from absorption of dark matter, not from 21 centimeter at all, but just the absorption of CMB by dark matter. But you can also have very interesting spectral distortions, which have a very different shape again from all the other distortions that I talked about earlier, and you can again do some parameter search. And also if dark matter is this multi-level dark matter, then dark matter is there in all along the universe. So if you look at quasars, when the quasar light passes through this dark matter, it will get absorbed. So just like Lyman alpha forest or 21 centimeter forest, we will have a dark forest. This is the edges part that I showed you. So you can choose parameters so that the edges anomaly can be explained with this model. And I think I am out of time. So I did not have time to talk about polarization, but it's a very interesting thing that there are free electrons in clusters, and clusters have velocity, and the line of sight velocity gives you the Doppler effect with the CMB scatters on these electrons, and the coherent velocity of all electrons in the cluster, or the peculiar velocity of the clusters, gives you a Doppler effect that is called the kinetic SZ effect. The transverse moment motion, linear order does not give you anything, but at second order it gives you a polarized SZ effect. And it is possible to detect this in next generation of experiments using the pairwise effect, so using the stacking of the clusters. And so you can look at these papers if you are interested in learning more. In particular, we can learn not about the line of sight, but the transverse velocities of the clusters also. So I will just stop with this slide. These are just what I have, the aspects that I have talked about earlier. I will just stop there. Thank you.
We have time for one or two questions. Yes. Yeah, please go ahead.
Okay, so the last slides that you showed with the CMB stage 4 constraints, so have you looked at just the Simon's observatory combination?
Yeah, so there is a Simon's observatory. I think I did not put it here, but we have put it, looked at Simon's observatory also. It is slightly worse than CMBS4, so it also does very well. This is actually a new effect we have proposed. So usually in pairwise KSZ effect, you pair cluster with cluster. But here we have proposed that if you pair cluster with galaxy survey, you actually boost the signal by signal to noise by quite a lot, and you can do much better. So these outer contours are the cluster pairs, and inner contours are if you pair these clusters with DAISY or with LSST galaxies. So you can actually improve quite a bit.
Thank you.
So I had one question. So this, you talked about that interaction of neutrinos such that the free streaming would be delayed. So does that also change something in the polarization spectra, or it just changes in the, this temperature spectra of the CMB?
No, so it will change polarization also, because this polarization also, we have the same acoustic oscillations. They appear at different scales, because polarization physics is slightly different. It is coming at slightly, it is coming from the velocity modes mostly, whereas anisotropies are coming from the density modes. So there is a phase difference there. But we have the same oscillations. So these are the oscillations which are getting phase shifted. So we have the same phase shift in the polarization also. In fact, if you are only phase shift temperature and not polarization, then you will have a disagreement, and because polarization will give you different parameters than temperature.
Okay, thanks.
Thank you. Unfortunately, we don't have time for more questions. We would request you to discuss during the coffee sessions. Let's thank Rishi again for his talk. Our next speaker is Tuhin Ghosh from NISA Bhubaneswar. He will be talking about lesson learned on CMB Foregrounds from Planck and Bicep.
Mr. Speaker.
Okay, good morning everyone. So my name is Tuhin Ghosh. So I will talk about lesson learned on CME foregrounds from Planck and Bicep. So these are the two experiments that I was associated with, Planck and Bicep experiments. So Planck stopped working in 2013 and Bicep is still taking data. So before I start, I'd like to thank the organizers for having me here. So Rishi introduced CMB. So I'm experimentalist or like observer. So basically how we can measure the CMB from ground or space. So Planck is like third generation CMB experiment which try to measure the CMB spectrum. But it's not the first one. Before that there was a WMAP and Kobe. So this CMB and measurement of CMB anisotropy started from 1990s. And in future there are two experiments which are proposed or planned. One is Lightbird, which was planned to launch in 2032. And from ISRO also there is something which is planned by the CMB community, which is CMB Bharat. So this is from the space, so basically to get the large scale CMB modes. But from the ground also there are a lot of experiments which are targeting the small scales to learn about the universe. So there is a Simons Observatory which is functioning now and is taking the data. There is a SPT and ACT which is collecting the data, and the Bicep experiment. So my talk is mostly focused on Bicep and Planck, but the techniques and all the things that I'm going to talk about is valid for other experiments also. Okay, so basically the goal of cosmologist or the dream is basically to measure this spectrum very accurately. So this is the CMB spectrum from the temperature. So basically there are noise or foregrounds, so you have to minimize all those to get these points very accurately. So these are the data points, and then there is a solid line which is the model. So this model depends on, so currently our understanding is the lambda serial model, but if you want to look beyond the standard model, you want to measure this spectrum very accurately. So this is for temperature, but the temperature now is, information is exhausted, so it's the experiment given one sky. Whatever moods we can measure, we already done it with Planck. So now focus is mostly on the polarization part. So CMB is like 10% polarized. So we measure the polarization because it's linearly polarized. We measure Stokes parameter Q and U, and we convert this into E and B modes. So with Planck, we measure this E spectrum very accurately from 30 to 1500. So at large L there is error. At small l also there are large error bars. So given this error bar, it's hard to constrain the cosmological parameters. So like epoch of radiation, which depends on this low L measurement. And so basically what in the next generation experiments are targeting is to measure this as precisely as the CMB temperature. Okay, so this is the E mode power spectrum, but we can do all the cross. So there is a TE power spectrum which is measured very accurately. There is a EB spectrum, so we can cross with E with B. So ideally, if there is no parity violation, it should be 0. But with Planck, it is finding some oscillatory pattern which gives hints about the early dark energy model. So currently, the goal is to measure this EE, BB, and the BB spectrum to as precisely as possible. Okay. So this is the proposed Lightbird experiment. So what it will do? So where there are errors are large. Basically, the next generation experiment is targeting to minimize the errors and try to measure those. So my talk is mostly focused on this BB power spectrum. So this BB power spectrum that we measure has two parts. One is the primordial B mode, which is basically tracing the primordial gravitation waves. And there is a lensing B mode, which is the leakage from E to B. So if you can measure this lensing B mode, or make a map of lensing B mode, we can directly measure the dark matter distribution of the universe. So that is one goal. Other goal is to measure these primordial gravitational waves. So basically all the experiment, future experiment is targeting this B mode power spectrum. So you can see there are large error bars, so we want to minimize those. So that is a dream. So basically you can set up an experiment and measure those. But the challenge is that when we do the experiment, it's not that we can see only the CMB. There are foreground emission from our own galaxy. So this galaxy emits in microwave frequency. So if you look at one frequency, you can will not know whether it's a foreground emission or background emission. Okay. So what people do is they measure not in one frequency, but in multiple frequency to separate out what is the background emission and what is the foreground emission. Okay, so the low frequency, it is mostly dominated by radio emission or the synchrotron emission, which dominates at low frequency below 30 gigahertz in that frequency range. At high frequency, there is a thermal dust emission, okay, so which dominate above 100 gigahertz. So if you look at 545 gigahertz, it's totally dominated by thermal dust. So CMB signal is like very less there. But we do this multi-frequency observations to basically know what is the background and what is the foreground emission. And it is not at large scale. So it is there in all the scales. So at large scale, these are diffuse emission. But if you go to small scale, there are extragalactic emission like cosmic infrared background anisotropies, molecular clouds. There are point sources like there are radio point sources, infrared point sources. So there is no clean band or clean scale where we can just observe the CMB. But for temperature, we at least the background we can see which is constant in this thermodynamic units, and whichever is fluctuating is like changing is basically the foregrounds. So this is for temperature. For coloration, the story is same, but unfortunately for coloration, we cannot see the background. So everything is within the foreground. So we need to subtract the foreground emission to get to the CMB. Okay. So basically goal is to take those observations and remove the foregrounds in some component separation way and measure this intensity Q and U map, which is clean from any foregrounds. So once we have Q and U, we can make polarization angle, what is like how the angle is related to the structure, or in terms of E and B, which will help to help in the cosmological parameter estimation. So that is basically the goal. So now there are two different kind of foregrounds for B mode study. One is synchrotron polarization, which produces B modes. So the synchrotron polarization is basically coming from cosmic ray electron, which is gyrating around the, our own galactic magnetic field, which is order of microwatts. So this is theoretically 70% polarized, but what we observe because of the projection effect is typically like 20% polarized, and people model this using power law model. So this Q and U, it follows this power law index beta S, and this beta S we know to very high accuracy, but it's not enough to go to the V mode. So there is a region to region fluctuation which is causing problems. And this synchrotron polarization, we cannot do it at very low frequency because there are Faraday rotation. So there is a lambda square dependent terms which will correct this synchrotron polarization. So it's very, like if you go to like 1 gigahertz, it's very hard to measure at the galactic plane what is the synchrotron polarization. So people generally measure this above 10 gigahertz to get a good template of synchrotron polarization. So this is one of the dominant foreground. Another is the dust polarization. So these are basically small dust particles made up of carbon and silicates, which is basically gyrating around the magnetic field, and it will basically in optical, it will absorb this light and emit in infrared frequency. So people initially thought that it should not be that much polarized. So in BICEP they consider it like 2 or 3% polarized, but what is observed with Planck is that it can be polarized up to 20%. So this is the observed polarization. In this way it is more polarized, but because of projection effect we see this 20% polarization, and this follows a modified black body spectrum. So it's a power law, but there is a temperature dependence. So we need to know what is the temperature of the dust. So now I'm just plotting the CMB spectrum that we are targeting, and on top of it, this foreground emission. So this is taken from Simon's Observatory science paper. So basically, if you go from 1% to 90% of the sky, so there are some clean regions where you can measure this lensing B mode above the foregrounds. So this is good news because we don't need to deal about the foregrounds, which has complex nature. But for primordial V mode, so here for some R of 0.01, any region we go, there is a foreground which is dominate over the signal. So without the foreground separation, we cannot measure the CMB V mode. And to separate the foreground, one frequency channel is not enough. So you at least have 2-3 frequency channels to know what is the foreground and subtract it to get to the signal. So this is what was the initial idea of Lightbird. So this was proposed by Katayama and Komatsu in 2011. So they thought that if you do 3 frequency channels like 60, 100 and 240 gigahertz, and if you know what is the spectrum of this synchrotron spectrum and the dust, so one is power law, one is modified black body spectrum. So using 3 frequency, we can just subtract the synchrotron and the dust part, and we can achieve their targeted sensitivity of 10⁻³ . So that is started the Lightbird discussion, and now it is like in a almost mature stage, which will fly in 2032. But this is a model dependent approach. So these models are derived from the data, and we don't know what is how accurate these models are, because these are simple analytical models. And if there are complexities, like if it's not a power law, it has some curvature, or there is not a modified blackbody spectrum, is there a 2 modified blackbody spectrum? Because of the error bars, we see only the 1. So it will, if the model does not match with the data, then these foregrounds will leak into the CMB estimation, and it will give you false detection of the CMB signal. So this was shown by Demarzilas in 2016 paper, that it maybe there are, we are considering the dominant ones, maybe there are other foregrounds which are not that dominating, and if you neglect those, it will leak into the CMB and it will produce a fake signal. Yeah. So that if you do it pixel by pixel, it's difficult. So what is the approach taken by the BICEP team? So they basically, instead of looking at the, pixel by pixel where the signal to noise is a problem, so you can compute a power spectrum. So then you can increase the signal to noise by taking lot of pixels, and you can fit a model which has a synchrotron, dust, and it can be in the power spectrum level. The synchrotron and dust can be correlated, so that is taken by this rho indices. So we can fit with this model of foreground plus some primordial V mode R and some amplitude of the lensing signal. So this is a 7-parameter fit which was done by BICEP from 2015. So I will show the result, but basically this model, if you do it, is simple. The problem is that all these are almost like power law, so it's degenerate. So unless you put a prior, that what is the value of typical value of beta S, beta D, is very difficult to get a unique solution. So there basically Planck comes into the picture. So from Planck we have a large scale mode. So we can measure what is the spectrum of dust on the synchrotron at from the large scale. So what is found is that this dust, they follow nicely power law. So this is one is the E power spectrum and one is the B power spectrum, and this E to B ratio is roughly constant. And this T spectrum is this correlation with E is also roughly constant with the sky fraction. So if you can write whatever that the complex information of dust into this power spectrum and derive into simple mathematical form, it helps in the component separation. So we found that it is following a power law, and this power law has some index which is normalized at L is equal to 80, and if you decrease with the sky fraction, it follows a nice power law model. It follows like I to the power I square relation, and the BICEP point is here. So it is within this cosmic variance. So whatever the dust which is expected from the large sky fraction, it applies to the bicep patch. And this EB spectra, which people are interested for early dark energy model, so this dust also produce this EB, non-zero EB. So this is something new. So when somebody claims that from CMB we are measuring EB spectra, we need to be careful that it's not the foreground leakage. So it can be the foreground which leaks into the CMB and can mimic a wrong early dark energy model. So but the EB spectra, this TB spectra is consistent with 0. Okay. So this correlation between dust and dust and the synchrotron, it shows up in the power spectra. So at high frequency it is a modified blackbody spectrum, at low frequency is a power law, and then when you do cross between high frequency and low frequency, there are some points which shows up here. So that is a large scale effect at low L, but when we go to high L, it decays down. So this dust synchrotron correlation tells about that they are basically tracing the same underlying galactic magnetic field. So that's why even the source is different, because the same galactic magnetic field is tracing. So there is a large scale correlation between them. So similar thing can be done with synchrotron also. So what is found that at low frequency observation, it also follows a power law model, and there is a E to B ratio which is like or B to E ratio is like 0.2. Yes, I will finish. So from the spectrum, if you have multi-frequency observation, we can measure what is the spectral index, and the synchrotron is depending on the sky fraction, it is roughly constant. So, but then there are small error bars on top of it. Okay. So these are the simple model, but then it can have a decorrelation. So it's not the correlation when we observe, it's not the same pattern that we see in different frequency. So the pattern can change, and it will mimic like a decorrelation. So this cross, whatever the power spectrum, it is less compared to what is expected from 2 auto power spectrum. Okay, so this is first detected by Planck, that if they detected it like 2 sigma in each mask, but if you consider all the mass, it is like greater than 5 sigma detection, and this is a problem. So in the previous analysis, this decorrelation was not considered, that the pattern can change with frequency. So ideally larger frequency will not help, so you need to have more frequency channels in a very closed band. So for current CMB experiment, this is one of the major challenge to deal with the dust decorrelation. So if in the power spectrum level, if there is a SED variation that is not constant, SED is varying pixel to pixel because we are taking the power spectrum average, we can write in this form, but in reality we don't know if this form is true or not. And the result that Bicep is claiming that R is less than 0.06, it depends on this dust decorrelation factor. So, so this value is without taking into account decorrelation. So once we account the decorrelation, the value shift from the value to a lower value. So currently it is not detected, but this is one of the main concern of all the CMB experiment, how much dust decorrelation is there. And at least 1% we expect, and even 1% is problematic for this value of R. Yeah. So just last few slides to flash the images. So in Bicep result from 2015, they only consider dust and the CMB. So from that they get a measurement of some likelihood that this is the value of R. When they collect more data at the lower frequency, they start seeing the synchrotron. Okay, so so once the more foreground is there, the value of R shifted towards close to 0. They collect more and more data to get a confidence that to shrink the error bars, but what is happening is that error bars is shrinking, but the value is shifting towards 0. So this is including 150 and 220 gigahertz, and then suppose the synchrotron, if you collect more data, 95 gigahertz with Bicep 3, the value is stabilizing, but it is whatever the original value from 15, it is 21, it is shifted to close to 0. And this is not including the decorrelation in the formalism. So even include decorrelation, it shifts bit to the lower value. And this implication is that this R says what is the model of inflation. So with the more precise measurement, we can start ruling out more simple model of the inflation. And with this, thank you. And this is a summary of my slides.
We have time for a couple of questions.
Thank you. Hi, Tukin. Thank you for the nice talk. So, at some point you had showed that the dust also had some alignment with the magnetic field, and I think the dust tries to align with the magnetic field. So, in which case, like, wouldn't if you measure the synchrotron and the emission from the dust, wouldn't they be correlated in a sense? Then you have like one less parameter.
But there is a line of sight effect. So dust is a local dust, so which is connected with the magnetic field that we observe.
Sure.
But the cosmic ray is tracing the full galaxy.
Right.
So, but you see the integrated effect for the synchrotron. So it's not one-to-one correlation.
So if you look at the synchrotron spectrum, like you get the spectrum by just doing that synchrotron calculation, and since you know the chemistry of the dust, that will already tell you like what the spectrum you expect. But these two things at least align.
Locally it is correlated.
Right.
But we are seeing the integrated effect. So we don't know from where it is coming.
I see.
So for synchrotron we are seeing a larger path length, and for dust it is a localized, because it goes as 1 over r square. So whichever is far away, it will not contribute to the dust emission or the map we see.
Okay.
But locally it is, yeah, it is correct.
Okay, thank you.
One more question. Go ahead.
Yes. Yes. So this is the Simon's observatory, which is basically targeting. So this blue points is basically from prediction from the Simon's observatory.
So they are targeting this 500 to 2000.
Yes.
And based on these assumptions, we extrapolate what the program will be.
No, basically to get to where the amplitude of the R goes lower and lower, so then we need to rely on the de-lensing. So we need to know this lensing beam mode very accurately.
Right. But we are assuming that our models which are based on this multiple things will extrapolate to the other.
Yeah. So it is defined by only one parameter, AL. So once we know this AL accurately, so then we can de-lens and get to any smaller value of R.
Thank you. Let's thank Tuhin again for his talk. Our next speaker is Harsh Mehta from TFR Mumbai. And Harsh will be speaking about discovering Axion-like particles using CMB as a backlight. Harsh, 13 plus 2. 13 plus 2, 30 minutes.
I'm audible? Yeah. Good morning everyone. I am Harsh Mehta from TFR Mumbai, and today I will be speaking on discovering axion-like particles using the cosmic microwave background. So first of all, why to probe axions? So axions or axion-like particles, they are hypothetical particles which are predicted by various beyond standard model theories. Now they possess mass, so they interest cosmologists in the form of being dark matter candidates. So, but the problem with them is that they require very high energies or sensitivities for production in both particle colliders. So this is where the weak interaction they may be having with photons comes in, and that is why we can use CMB here, because CMB we know that it has a temperature of around 2.7 Kelvin and it follows an almost ideal black body spectrum as can be seen in this plot. So also the angular variation of the CMB is very well studied. So any deviations that arise in the CMB, they can be used to detect or probe ALPs. So now coming to the phenomenon that we are interested in, and that is the CMB photon ALP resonant conversion. So the photon ALP Lagrangian is defined using the ALP coupling, which is the GA gamma factor here, the axion field A, and the E dot B external term, which refers to the polarization of the photon parallel to the transverse magnetic field or the external magnetic field. So now this phenomenon, it takes place where the resonant condition is met, which gives us the equation that the effective masses of the ALP and photon are equal, and that is given using the plasma frequency or the electron density at the particular location. So what happens is that the incoming CMB photons, as they pass through the galaxy cluster, then in the presence of the transverse magnetic field, the polarization for some photons is lost, and effectively the CMB gains a polarization from being earlier unpolarized, and ALPs are formed. So the probability for this conversion, it depends on the photon ALP coupling, the transverse magnetic field, the frequency at the redshift of the cluster, and the electron density via the plasma frequency. Now the observable effect that is seen in the CMB due to this phenomenon is that the CMB gets effectively polarized, and also there is a change in the CMB intensity which depends on the probability of conversion, and it is also frequency dependent, and that is why we say that this phenomenon leads to a polarized spectral distortion in the CMB. Now this phenomenon can be studied either using resolved galaxy clusters which are resolvable in multiple frequency channels, or using unresolved clusters, those which cannot be resolved in multiple frequency channels, and I will go through them one by one. So for the case of resolved clusters, we use multiband observations. Now why multiband observations? Because we know that the probability of conversion, it depends on the photon ALP coupling, then the transverse magnetic field. Now this transverse magnetic field we can infer using radio frequencies. Then comes the redshift of the cluster, which you can get using optical surveys. The electron density or the plasma frequency we can get using X-rays or Sunyaev-Zeldovich effect, and then using microwave observations of CMB we can get constraints on the ALP distortion signal. So now using synchrotron observations, which we know refers to the acceleration of relativistic electrons in a magnetic field, so we can get the transverse magnetic profile of galaxy clusters. So we can use SK observations here, and then you can get the electron density and temperature profiles of the cluster using X-ray emission, which effectively is thermal Bremsstrahlung emission. So using its spectrum we can get constraints on the electron density and temperature, say from eROSITA observations. Now the effect that is caused in the CMB, so this is dashed line refers to the cluster region, and here if there are no ALPs in nature, then this is what the CMB will look like, and it will be kind of smooth. But if ALPs exist in nature, then there will be additional fluctuations in this cluster region which will increase its frequency. So if we take this map and take a spherical harmonic transform of it, then we can get the ensemble average of its spherical harmonic coefficients to get the power spectrum. Now this power spectrum, this is how it looks like. So at high L, which are the multipoles which correspond to low angular scales which galaxy clusters occupy on the sky. So since the galaxy clusters occupy low angular scales, we will look at high multipoles, and we see here that the CMB power decays down, but the axion power, the ALP signal power, it increases. So this is what we will look at, and it also increases its frequency as can be seen in this map as well. And these are the power spectra for different signals that will be contaminating our ALP signal, which are CMB, dust, synchrotron, and the noises. Now coming on to unresolved clusters. So here what I have done is I have stacked the matter density fields at various redshifts, and the over density regions in the matter density field, they correspond to cold spots in the CMB. This is because the ALP conversion leads to a loss in the CMB photons or the CMB intensity. So the ALP distortion signal, it is generated in galaxy clusters which are embedded in dark matter halos which make up the matter density field in the universe. So we can model galaxy clusters as halos of mass range from 10 power 13 to 7 to 10 power 15 solar masses, and we will be doing an halo modeling of it. Now coming on to the diffuse background that we get. So the CMB photons, as they travel through the large structure of the universe with many clusters at different redshifts and of different masses, then we will be getting the photon ALP resonant conversion in them and effectively a ALP diffuse map. So from this map we can take the harmonic transform to get its power spectrum, and we see here that here as well we see an increase at high multipoles. So this is the change that is causing the CMB due to these unresolved clusters, that here again you will see additional fluctuations at small angular scales, and the power will increase at high multipoles. So this increase in power, it depends on the photon ALP coupling. The higher the strength, the higher will be the rise in power. Now here I have plotted the spectral and spatial variation of the various signals. So we see that the ALP signal, it increases with frequency. The CMB, it almost stays constant with frequency. The galactic dust emission, it increases with frequency, but it follows a much different spectral and spatial behavior than the ALP signal. Then the synchrotron emission, it decreases with frequency. So this spectral and spatial behavior we can use to separate the ALP signal from the different components. Now, until now we have looked at the homogeneous profiles for spherically symmetric clusters, but that is the ideal case, but we won't have necessarily the ideal case, and we will be having turbulence in those profiles. So how can we quantify that? So we will be using the length scale that are involved. The first is the photon ALP oscillation length scale, the electron density variation scale, and then the magnetic field variation scale. Now the first two length scales, they enter into the calculation for the conversion probability, but the third length scale, it comes in when we calculate the polarization signal. Now this is because the alignment of if the magnetic field domains are misaligned, then that will lead to a depolarization of the polarization signals from various resonant locations, as the ALP signal will be forming in those locations. So that will lead to a depolarization of the ALP signal. So now we have developed a setup that will take into account this turbulence, and so here I have shown that due to an increase in or decrease in the domain size, we will be having a change in the polarization signal but not the temperature signal, and the polarization signal, it decreases as the domain size decreases of the magnetic field. Now here I have taken Gaussian turbulence in the strength of the magnetic field, and here we see that the spatial extent of the signal remains the same, but the fluctuations increase as the turbulence in the magnetic field increases. And then this is the case for the electron density turbulence, and here we see that not only the strength changes, but the spatial extent of the signal also increases as more and more resonant locations, even in the outer regions of the cluster, give us the signal. Yeah, thanks. So now the other observables that can be used. So one is the cross temperature polarization power spectrum. Now this will follow a distinct frequency dependence, which will be irrespective of the turbulence that is within those clusters. So this can be used to model the ALP signal from various clusters. And the second thing is the non-Gaussianity of the signal. So the ALP signal is highly non-Gaussian, and the non-Gaussianity of the signal will change with the turbulence in the cluster. So we can look at different cluster regions, and we will see that there is changing non-Gaussianity signals from the various cluster regions as opposed to the Gaussian nature of the CMB, which we usually get to see. So now how well can we measure the signal? So we can get a SNR of around 4 with CMB-S4, and with CMB-HD we will be getting a SNR of around 92. And when we convert this into constraints, then we can get, with CMB-S4 we can put bounds of up to 10 power minus 12 per giga electron volt using CMB-S4. So, and this is for the case of ALP mass range from 10 power minus 15 to 10 power minus 11 electron volt. Now if we just consider, for the case of resolved clusters, if we just consider that a particular ALP mass is forming, say 10 power minus 13 electron volt, then we here show that we can get bounds more than an order of magnitude better than the current bounds from cast. So this 66 line here is the bounds from cast, and this is the bounds that we are getting. Now here we see that we can, using the CMB, we can also get a lower limit if there is a non-zero ALP signal in nature. So this is the pipeline that I have developed, and that is called Spectrax, and it can use radio, optical, X-ray and CMB observations to infer galaxy astrophysics and constrain the ALP coupling. So now finally coming to the ALP conversion in the Milky Way within our own galaxy. So we know that the Milky Way, it has very turbulent profiles, so they will be impacting our ALP signal. Also our ALP signal is highly non-Gaussian, so we cannot use the power spectrum to get all the details of it. Now the problem is that foregrounds themselves are also very non-Gaussian. So how to model the ALP signal? So we would require computationally expensive 3D simulations, but that would be just too much. And so we have developed a spatial sky-based technique which will capture the non-Gaussianity and the large-scale behavior of the ALP signal. So here we take a crude model and we try to model the ALP signal that we expect. So this is the crude model that I fit to the ALP signal, and it kind of works very well, as it can give me the constraints on the ALP coupling of up to an order of magnitude better than the current bounds from cast. Now this modeling, it is not like it is just accurate enough. So we can take a patch-based analysis. We can do a patch-based analysis where from different patches we can get the coupling constraints, and using that we can either model it better or remove any systematics that are involved. So finally we can detect ALPs using a large number of clusters from CNDS4 or Simons Observatory, and then using the galactic signal from LightBird. So combining all of them will give us much better bounds than expected, and then we can use our pipelines on data from upcoming telescopes and to study other cluster phenomena such as SG effect and synchrotron emission. And these are the relevant publications. All of these are published in JCAP. And I would like to thank my supervisor Subodhi Mukherjee, the Data Theory Universe Lab at TFR, and the Cosmic Connections team. Thank you.
Thank you, Harsh. Quick couple of questions, one or two questions. Yes.
Hi, thank you for the nice talk. So the magnetic field that you consider in these galaxy clusters, sorry I might have missed this. Like, what is the spectrum, like spectral profile for this? Like you take Gaussian.
For the synchrotron emission?
I mean, yeah, sure.
Yeah, this one. The power law dependence.
No, but at some point you were saying that the ALP signal would depend on how the spectrum of the magnetic field is in your cluster. You were talking about like misaligned domains and stuff.
Okay. Oh, I see. Yeah, this one?
Yeah.
Yeah, so if we have, now we know that the polarization is caused due to the direction of the magnetic field. So if the magnetic field is very much misaligned,
so this is on the scale of the cluster, is it?
No, it is lower than the size of the cluster. It is very low than the size of the cluster. So if it is very turbulent, then we will have very low domain sizes, and that will cause a lot of depolarization of the signal.
Thank you. Any other brief question? All right, let's thank Harsh again. Thank you, Harsh. Our next speaker is Purushottam Ghosh from IMSC Chennai. He'll be talking about CMB precision cosmology, insights into BSM physics.
Okay, I will take.
Purushottam, 13 questions.
Okay.
Okay. Hello everyone. Let me first thanks to the organizer. So this talk is in the interface between the particle physics cosmology, slightly different from the earlier talks. Okay. So the main idea of this talk, if we have a BSM interaction between the standard model fermion and the light mediator, Then the light mediator faces several constants from different experiments like laboratory experiment, cosmological observation and astrophysical observation. So our objective is here to identify the region of parameter space where the cosmological observation ineffective, I am talking about the ineffective coming from the Planck data put a stringent constant. So this is a cartoon figure in the plane of mediator mass and the coupling. So this red line is our point of interest. So it corresponds to the ineffective upper bound from Planck data, and the left region is this figure from the Planck observation. Okay, so let me start this figure. This is very well known figure to all. So it shows the history of the universe across the different epoch. So in this talk, I mainly focus the epoch between after BBN to recombination, where the temperature is spanning from few MeV to EeV. So during this period, neutrinos are decoupled from the thermal plasma, and this phenomena associated with the parameter called ineffective is defined as the energy density between the neutrino bar and the photon bar. And Planck 2018 data precisely estimate this ineffective value at CMB assuming lambda CDM cosmology. Okay. So let us discuss our understanding of ineffective based on the standard model particle physics. So this is the effective interaction associated with the neutrino and the electron positron. So at the high temperature, let's assume the temperature around 10 MeV, neutrino and photon both share the same temperature. As temperature drops, universe expands, the weak interaction rate fall faster than the electromagnetic interaction rate, and therefore neutrinos are decoupled from the photon bar. So at temperature below electron mass, the electron positron entirely annihilate to the photon bar. So therefore there is a rising behavior here in the photon temperature correspond compared to the neutrino temperature. If you go further lower temperature, so then this ratio becomes saturated. So once you know this ratio, then you can find out what is the value of the ineffective using this simple expression. So within the standard model, it turns out 3.043. So therefore we have the Planck observation and the standard model prediction. It shows that there is an additional contribution to ineffective which is around 0.28, and that indicates the scope of new physics. Now the question is what kind of new physics can accommodate this additional ineffective contribution. So there are different approaches addressed in the literature. In this talk I will discuss the non-standard interaction of neutrinos and electron positron with the light gauge boson. So these light gauge boson are the very popular candidate in the context of the particle physics, and they arises from the various anomaly free U1X models. So these are the very popular U1X model studied in the different aspects of the particle physics. So what we have done, so instead of considering individual model, we start from the generic U1X model, and as you know, there is if we consider specific charge assignment, that leads to this all anomaly free U1X model. Okay. So therefore the presence of the Z prime, so this is the relevant interaction for our discussion, and here Z prime form a different bar along with the photon and the neutrino bar, and Z prime act as a bridge between the neutrino and the photon bar, and it's also try to maintain the energy density neutrino and the photon bar via the scattering and the decay. So this is the temperature ratio plot. So the blue one, as I discussed before, this is purely standard model one. So the presence of the Z prime, so it corresponds to the red one. So the presence of the Z prime, neutrino bar temperature increases compared to the photon bar temperature. So therefore this ratio is decreased, and that leads to the larger N effective value. Okay, so now we'll try to understand how the generic the parameter, the U1 generic U1x model is important deciding the N effective value. Okay, so this is the important parameter. So since we are talking about the light gas version, the mass and coupling is important, and since we are talking about the generic U1x scenario, so this x1, x2, x3 plays a crucial role deciding the value of N effective. So this x1, x2, x3 is associated with the first, second, third generation of the lepton in the standard model. Okay, so let's discuss this plot. So this is the N effective variation of N effective as a function of the coupling. If it goes, if for the with the increase of the gas coupling, the N effective value increases. So that is because your interaction rate increases. And this shaded region is disfavored from the Planck data. So it shows that this plot shows that the higher couplings are basically disfavored from the Planck observation. Okay, so there is a very important points in this plot. So this particularly in this blue and the green line, so that corresponds to x1 not equal to 0. So that means this interaction is present. So if it goes from blue to green line, the effective charge dx times x1 increases from 1 to 3. So therefore the green one is the higher N effective value. On the other hand, for the case of x1 equal to 0, when this interaction absent, I mean the Z prime interacting with the photon bar is absent, so then it shows something peculiar behavior. So this is because in the lower coupling region is purely decay, and the higher coupling region there is a competition between scattering and the decay. So therefore, depending on these x1 numbers, one can categorize this the all U1x model two category. In the first category, when x1 not equal to 0, that means Z prime do have the T level interaction with the electron positron, and these are the U1x model fall in this category. And in the second category, where x1 equal to 0, where Z prime doesn't have T level interaction, this interaction absent, doesn't have the T level interaction with the electron positron. However, they can interact with electron positron via induced coupling, surface induced coupling. So these are the U1x model fall in this category. So for our discussion, we consider all type of U1x model. Here the green highlighted one corresponds to x1 not equal to 0 and rest of x1 equal to 0. So let me discuss one of the important outcome here. So this is the plot, the N effective, delta N effective, variation delta N effective as a function of the Z prime mass. So with the increase of the Z prime mass, the N effective contribution is decreases. So this is because at the higher Z prime mass, the number density of Z prime is self-suppressed. So again, this shaded region is basically disfavored from the Planck data, and it shows that lower Z primes are disfavored from the Planck bar. So here you can see the three distinct lines, and with these three distinct lines you can generalize all U1x model basically considered in the particle physics. In the lower one is corresponds to x1 equal to 0, and the middle one corresponds to x1 equal to 1, and upper one corresponds to x1 equal to 3, and these are the corresponding U1x scenario. If he goes for a given Z prime mass, if he goes from lower to upper, so the x1 value increases, that means the effective coupling x1 times gx increases, so therefore the N effective also increases. So this is the plot. Here we plotted the N effective upper bound in the plane of mz prime mass and the coupling. So this red line is the N effective upper bound from Planck, and this is our point of interest. And the left shaded region, the red region, is basically disfavored from the Planck data. And in order to compare how this constant is relevant for compared to the other existing constant, we showed some laboratory constant, it shows that there are some region, the ineffective put a more stringent constant than the others, like the middle, this region and this region. Okay, this is the case for B minus 3 LE. So what is the difference between from left figure to right figure? So here x1 charge changes from 1 to 3. So therefore this red line shifted towards the higher mass, higher mz prime mass, and accordingly the other constant also changes, and same for the other two scenarios. Okay. So this is the case for x1 equal to 0. Here also we plotted the ineffective upper bound, that is the red dash line. So here, as I said, x1 here x1 equal to 0, but z prime interact with the electron positron via induced coupling. So if you allow the some non-zero induced coupling, it's behave some peculiar behavior. That is because as I mean the competition between scattering and decay. So with this, I would like to summarize. So we start from generic E1x scenario, and then we come to the different E1x model, and each E1x scenario we identify the exclusion region or ineffective upper bound in the plane of mz prime and gx. And these E1x model are widely used in the particle physics community. We hope these bounds are highly relevant. And the futuristic bound like CMBS4 CMBS4 are expected to put a more stringent constant on the parameter space of the light gas boson. Thank you for the attention.
Thank you, Purushottam. Time for a couple of questions.
Hello. On slide 11 is shown 4 plots, and first plot we have epsilon 0, and we do not see any z prime dependence on z prime, and the next plot we have some peculiar behavior.
Okay.
So would you?
Yeah. So it's a it's a good point. So the first plot. So there, as I said, x1 equal to 0, there is a no T-level coupling with the electron positron. This is the first point. And the second point, when you consider epsilon equal to 0, so there are even no induced coupling with the electron, loop level induced coupling. So there is a no coupling to the photon bar. Okay, so therefore the whole energy density of the z prime entirely annihilate to the neutrino bar. So it's a basically 100% branching. So therefore there is an independent behavior in the GS coupling. So there is a 100% branching. So it's there is no other branching available in the bar. So therefore is an independent behavior. On the other hand here, so here is a induced coupling. Always this is suppressed, but due to induced coupling, so you can see here this is the independent behavior. Again there is a variation on Gx and mz prime. So that is again because there is a competition between the decay and scattering at the higher coupling. Yes.
Okay, thank you.
Thank you. Just speak into the microphone.
So mass of this Z boson, are you getting the mass by using standard Higgs mechanism? This MX.
So this is the U1X symmetry breaking. So
yes.
This is additional U1X.
Yeah, how do you get this non-zero MZ prime? Because this is gauge boson.
Gauge boson. So
yes.
In order to get mass of the Z prime, you have to break the symmetry of U1X. So this is apart from the standard molar symmetry, there is a we consider U1X symmetry.
So you have to introduce another new Higgs into the system.
Another Higgs. Yeah, you need an additional Higgs.
Additional
singlet scalar.
Okay.
And that's basically.
Okay, thank you. We need to move to the next talk. Let's thank Purushottam. Our last speaker in this session is Abhi Bhattacharjee from HRI Prayagraj. He will be talking about forecasting constraints on non-thermal LIMRs from CMBS.
Mm-hmm.
13 plus 2 minutes.
Okay.
So hello everyone, I'll talk about forecasting constraints on non-thermal LIMRs from future CMB experiments. And this talk will be based on this work which I did with my supervisor Anshuman Maharana, Orka Banerjee, Shubhinoy Das and Ravi Kumar Sharma. This is a plan for my talk. First I'll give some introduction and motivation for our model, and then talk about for our work, and then I'll talk about our model, and then discuss about Fisher analysis, and talk about my results and discussions. And then I will talk about higher moments of the distribution function. What this is will become clear when I move into the talk. And finally, I will conclude my talk. So the total radiation energy density in the universe post neutrino decoupling, or more specifically after electron positron annihilation, is given by this expression. Here n effective is called the effective number of neutrino species, but as we will see that it can have contributions from extra relativistic particles which have nothing to do with neutrinos. The standard model prediction for n effective is 3.044, but from DCY plus CMB measurements we get this value at 68% confidence level, and this indicates that there is room for non-zero delta n effective, and future experiments will probe delta n effective with even greater precision. Generic feature of many beyond standard model proposals is the presence of new light relics which behave as dark radiation and contribute to n effective. Sterile neutrinos which have been proposed to address anomalies in neutrino oscillation experiments are a candidate, but a fully thermalized forced sterile neutrino which follows the Fermi-Dirac distribution, that is not allowed. But hot thermal relics which decouple from the thermal plasma prior to neutrino decoupling, they are allowed, and their contributions to delta n effective are given here if we assume that they decouple prior to at a temperature greater than the mass of the top quark. And for massless relics, the cosmological impact is completely captured by this delta n effective parameter, and Benjamin Wallish with Daniel Baumann and others have worked on this. The other possibility is that of light massive relics, massive particles which contributed to the radiation energy density in the early universe and to the matter density at late times. And future forecasts from future experiments for thermally distributed scalar vector while Fermi-Dirac Fermi relics have been performed by Linda, Zhu and Deporzo and others. Now, the influence of light massive relics on linear cosmological observables can be characterized by three parameters. Delta n effective, this represents the contribution of the LIMRs to the relativistic energy density of the universe prior to recombination, and MSP effective represents the contribution of the LIMRs to the total energy density today, and AFS, this is the free streaming velocity of the LIMRs. From here we see that of the three, only two are independent, and for our work we consider delta n effective and MSP effective as the phenomenological parameters to investigate their impact on linear cosmological observables. Now coming to our model. So we consider the decay of the inflaton or moduli mostly to the standard model sector and partly to the dark sector, which leads to a transition from an early matter dominated era to radiation dominated era in the early universe. And due to interactions, the standard model sector that is fully thermalized, but the sterile sector is not thermalized. And we consider the decay to the sterile sector to be of this 1 to 2 decay with a branching ratio BSP. The late time distribution functions of the non-thermally distributed sterile particles LIMRs was found in this paper by Sukanya Bhattacharya, and this is of this form. E hat is the energy of the sterile particles at production, N0 is the initial number density of the inflaton or the modulus, this is the branching ratio to the sterile particles like I mentioned. S hat, this is just the scale factor as a function of theta, which is a dimensionless time parameter defined as T over tau, tau being the lifetime of phi. And each is the dimensionless Hubble parameter. Y is defined in this way. Here theta star indicates that by this time all the phi is assumed to have decayed, and Q is the momentum in units of the typical momentum of LIMR today, and this quantity N0 can be expressed in terms of the CMB temperature. Our model has four microscopic parameters. One is BSP, the other is MSP, and M phi, which is the mass of the inflatonal modulus, which we take to be of the order of 10 to the power minus 6 Planck mass, and tau we take to be of the order of 10 to the power 8 over M phi. The phenomenological parameters have these expressions. Here MSP is the physical mass of the sterile particle. And we also compare the results with a simple distribution function, the Robinson distribution function. So non-resonant active sterile neutrino oscillations in the early universe in the limit of small mixing angle gives rise to this expression for the sterile neutrinos, this momentum distribution function, which is just a rescaled Fermi-Dirac distribution. And in the limit of instantaneous neutrino decoupling, the phenomenological parameters take these forms. This shows a comparative plot of the inflaton decay model distribution, which I denote as NT non-thermal, and the DW distribution. And this has been plotted for same values of the phenomenological parameters. For this plot, we chose delta N effective to be 0.034 and MSP effective to be 0.903 electron volt. The corresponding model parameters are shown here. This is for the non-thermal model and this is for the Robinson-Woodrow model. So a reminder of the basics of Fission analysis. So the idea is that if we have a set of data and a model M with a set of parameters, we can readily compute the probability of x given theta. But how do you compute the probability of theta given x? Bayes' theorem relates these two. This p theta x is called the posterior, this p theta is called the prior, this is called the evidence, and px theta, this is called the likelihood, which is defined as the probability that experiment yields the observed data given a theory. And in the limit of large amount of data, the likelihood can be expressed in this Gaussian form. Here C is the data covariance matrix and X is the data vector of dimension n. The Fisher matrix is formally defined as the curvature of the log likelihood function evaluated at the fiducial values of the parameters, and this quantifies the amount of information that a given experiment can provide about a set of parameters. So it's called forecasting. So it shows if the curvature is high, then the constraints will be tighter, and if the curvature is low, the constraints will be wider, and the error will be greater. The error estimate, the error covariance matrix is defined as the inverse of the Fisher information matrix, and the marginalized 1 sigma uncertainty of the parameters is given by this, the square root of the diagonal elements of the covariance matrix. The non-diagonal elements determine the shape and size of the error ellipse in the parameter plane. Now for CMB experiments, the Fisher matrix takes this form. For 12 plus 1 is the number of modes per L. This is the fractional sky coverage for the experiment. CL is the spectral covariance matrix, which is shown here. And this includes the Gaussian noise for temperature and polarization. Here S is instrumental noise in temperature polarization, and theta W is the resolution of the experiment. And NL55 is obtained from the minimum various combination of various quantitative parameters. So the fiducial model for analysis consists of these 6 lambda CDM parameters and these 2 phenomenological parameters. We consider 2 sets of fiducial values. The first one corresponds to the best fit of MCMC with Planck 18 and S8 data sets performed in this paper for being performed with the model. And set 2 corresponds to the mean values of the 6 lambda CDM parameters from the Planck 18 paper for the lambda CDM model extended by delta N effective and MSP effective. And unlike for set 1, in set 2, in the Planck paper they used this prior on the mass of a thermal sterile particle, which leads to these bonds on delta N effective and MSP effective. And this quantity is related to a phenomenological parameter MSP effective by this relation. So this shows a comparison of the residuals of theta and phi spectra. Increasing delta N effective just leads to more damping of the CMB tail as expected, and even though for set 2 the mass is lesser, so the free stream velocity is greater, but the suppression is less. This is because in set 1 a greater part of CDM is replaced by Larry mass, and so it has less stress strain component and hence more suppression. This shows the experimental parameters which are used for a Planck and a particle was done by CMB stage 4 experiment. This one is in microkelvin arc minute and this is in arc minute. And we consider the results from the joint analysis of Planck and CMB base 4. We added these 2 Fisher matrices to ensure that we don't double count in the region of overlap. We get these results for the phenomenological parameters. First thing we notice is that for both the non-thermal and Robinson-Woodrow models, with a similar constraints on delta effective and MS effective, and this is true for both sets. This shows the Fisher plots for these parameters, omega m is omega b plus omega c d. This is the but for set 1, the return rated MSP is slightly degraded as compared to set 2. Delta effective and MS effective are positively correlated for set 2, but they are negatively correlated for set 1. And delta effective and H are negatively correlated for both sets, which is unlike in the case of standard neutrinos where they are positively correlated. This shows the evolution of the LIMR energy density. Set 1 corresponds to the Haber LIMR, which contributes lesser to the radiation energy density due to its lower abundance, but comparatively greater to the matter density compared to set 2. This shows the evolution of decretion of state parameter for the LIMR. The blue curve, it corresponds to set 1. We see that this Haber particle becomes non-relativistic just before matter radiation equality, and at the time of recombination, it contributes totally to the matter density. And for set 2, on the other hand, we see that it has still some non-zero contribution to the relativistic energy density, and as such the Haber LIMR, it becomes sensitive to CMB almost exclusively through its effect on the weak length signal. Sorry. So in your paper we have used these and tried to explain our results. So we saw that when we matched the first two moments which are related to the two phenomenological parameters, we obtained similar results for the non-thermal and Rodolphin distribution. And to include the effect of a higher moment, we considered an Edgeworth-like expansion about Rodolphin video distribution. For PEM, these are mth order polynomials which are orthonormal with respect to a measure q square over a to the power q plus 1. This we can write simply as alpha plus beta q plus gamma q square. And when we match the first two moments of f and fdw, then we can write alpha and beta in terms of gamma. And f, which earlier had one parameter chi, now has two, chi and gamma, with the requirement that the meaningful distribution function has to be non-negative, restricts the range of gamma to this. And gamma equal to 0 corresponds to Rodolphin video distribution. Here I have plotted the modified distribution with matching first two moments, but the third moment refers to the maximum possible extent. Again, we perform Fisher analysis with the 6 lambda CDM parameters and delta n effective, MSP effective, and gamma. And this figure shows the results. And we see that a significant overlap between the positive distributions for the two models with gamma equal to 0 and gamma equal to 0.25 indicate that any CM-based-like experiment is unlikely to distinguish between these models. However, from our results for a hypothetical cosmic variance limited experiment, it indicates that a future experiment with better sensitivity can potentially distinguish between these two. Now I will conclude. So you see that the constraints on delta n effective as well as delta n effective and MS effective degeneracy directions depend on the time of non-relativistic transition. For a heavier LIMR, which becomes non-relativistic well before recombination, delta n effective is more tightly constrained. And that is owing to the fact that changes in omega m and omega sp at recombination cannot be replicated by changes in delta n effective. We obtain similar constraints for two different models with visibly different distribution functions once delta n effective and MSP effective are matched. Furthermore, two models with matching first two moments, even with maximally varying higher moments, cannot be told apart by CM-based-like experiments. And combining CM experiments, galaxy surveys like LSST and Euclid, as has been done by Depozo and collaborators, and going into the nonlinear matter power spectrum, can break degeneracies and reveal signatures tied to the LMR production mechanisms, which our linear analysis is inherently insensitive to. We use these packages class or fix and fish chips. And with this, I'll end my talk. Thank you.
Thank you, Abhi. Time for a question or two.
So I have a very naive question. So because these LIMRs, they act as relativistic particles in the early universe and become massive later, so how will your results change if you include the DAISY data? Because it kind of, it says that omega n is lesser than expected. So, I mean, how would your results change if you included AZ data?
Okay, I don't think I'll be able to tell that if we include this data. I don't know, I have to see.
Okay, thanks a lot.
Ranjan.
Hi, thanks for the nice talk. I have a probably a more model-dependent question. So
Okay.
you are producing these non-thermal light massive relics from inflaton decay.
Yes.
So is there any relation so since presumably inflaton also produces the standard model particles, is there any relation between these particles or coupling between these particles and the standard model?
No, we are not considering any coupling. We say that the inflaton decays mostly to the standard model sector and partly to the dark sector with a small branching ratio, and there is no interaction between these two, between the dark sector and the standard model sector.
Okay, thank you.
Any other brief questions? If there are none, let's thank Abik again. We now break for coffee. Coffee will be served just outside. We finished a few minutes late, but we'll try to start the next session on time. We will be back here at 11:30. Thank you.
Hello. Hello. A quick announcement. So the next chair will be Kanun Dotto, and then I'm going to announce the chairs of the consecutive sessions. But if you are not available to chair the session, please let one of the LOC member know, and they will swap your chair session with somebody else. So the session 3 after lunch will be chaired by Professor Anjan Ananda Sen. Then Supratik Pal is going to chair the flash talk sessions in the evening. So we have to, okay, I'll check if Supratik Pal has already come or not, but yeah, we go to the next session.
Welcome to the second session of the first day. We have 5 talks in this session. The first speaker is Dr. Suman Majumdar from IIT Indore, and he is going to talk about cosmology via multi-wavelength intensity mapping. Suman.
Yep. I would like to first thank the organizers for giving me this opportunity to present our work here. So today I talk about multi-wavelength line intensity mapping and how you can do cosmology with it. And I will start with pretty early phase of the universe, and eventually we will come closer to the present day. So the first phase that I will talk about, the cosmic phase, is the epoch of reionization, which is essentially the period when the first sources of lights like galaxies, quasars, and first and they gradually ionized and heated the intergalactic medium. Obviously, it would be great to see the IGM as well as these sources all together with highest resolution and details possible, but that's not necessarily the case. Even with JWST or ALMA, probably you will be able to see only the sources which are extremely bright in this particular period. However, as we all know, more or less, the belief is that the faintest galaxies are the one which are numerous and probably has driven the reionization most of the cases or models, let us say. So the challenge is how to observe those galaxies or their impact or those sources' impact on the reionization. So essentially there comes this unique technique which has been in the field for quite some time, and it is being used particularly for observing the IGM, particularly using 21 centimeter line. However, for the sources, this is slightly new compared to the IGM observations, and that is using unique line emissions from the galaxies. Essentially you can probe these galaxies. And how do you do that? Even for a faint galaxy, if you make a big pixel or voxel and add up all the emission from of a particular line being emitted by a bunch of galaxies that are lying within that voxel, and paint that voxel with that integrated flux, essentially you get a bright cell or a empty cell, essentially. So using this, you can make a coarse-grained image of the sky of that particular line that you are targeting. So now if you choose your lines judiciously, that line might be associated with the star formation rate, etc., and might help you to understand whether that type of galaxies were, means the lines emitted, what kind of galaxies were dominant at what time. Essentially you can forward model this process and do all your interpretation. So essentially the idea is that the large scale structure is galaxies are the biased probes of large scale structure. You are unable to detect individual galaxies at high redshifts or the faint galaxies. So you make a coarse grained image using line intensity mapping. Now you can choose various kinds of lines, and depending on your instrument, if it is concerto, you target the singly ionized carbon. If it is COMAP, you target CO, redshifted CO line, and if it is Sphere-X, which is launched a few months ago, essentially which targets various kinds of laminar alpha and other lines. And for IGM, then you can target the neutral hydrogen 21 centimeter line. And effectively the maps that you will get out of it would be something like this. This will how the sources look like, and this is how the ionized IGM or ionized and neutral IGM would look like. And once you have those observations, you would like to interpret them. To interpret them, you need to build forward models, and these forward models will involve simulating the large scale structure and then painting these halos with particular line emission depending on the star formation rate in those halos, depending on the model of star formation that you choose. Similarly, you can post-process the dark matter density field and the sources and produce a H1 map as well, 21 centimeter map as well. So one former PhD student at IIT Indo, Chandrasekhar, along with me and Kanan Datta here, has done a bunch of work on this particular domain, where he essentially developed a tool to simulate both the C2, CO and 21 centimeter line from the epoch of reionization. So the first work that he focused on essentially was what is the impact of the light cone effect? What is light cone effect? It is essentially the evolution of the signal along the redshift axis or along your line of sight. Now, when we interpret these observations, we may or may not include this particular effect. The signal evolves along the cosmic time, right? So the evolution is more or drastic in case of the IGM signal, whereas the source signal, this line intensity map, you don't see that much evolution because structures basically evolve rather slow compared to the state of the IGM. So what if you include this particular fact in your forward model and you don't include, and what happens to your interpretation? So we looked at something called the cross power spectrum of C2 and 21 centimeter signal, and by including this particular effect inherently in our simulations as well as not including it, and if you do not include it, the change in your interpretation becomes more than 20% or so in sufficiently large scale. It depends on the history of reionization as well. If your reionization is fast or slow, that actually tells you whether this light cone effect will be significant or not. So it's better to include it for interpreting your signal. That was the more or less conclusion. Now there is something when you are doing this forward model that we generally ignore, not always, but generally ignore, is that there is a line luminosity halo mass relationship, and this is more or less an empirical relationship people use. Now, while using this empirical relationship, people do not take into account the astrophysical scatter that might be there in that line luminosity halo mass relationship. Now, this astrophysical scatter may depend on depending on the environment of the that galaxy from which this line is being emitted. So we picked up some hydrodynamical radiative transfer simulation, SIMBA, and which was processed by a chemistry code called SIGAME by a group in Copenhagen. So, and we looked at this line luminosity and halo mass relationship that they had published. So, and you can see there is a significant scatter. Now, if we include this scatter, this arises due to this multi-phase state of the ISM. If we include this scatter in our forward model, how do we include it? First question, and then whether that has an implication in your interpretation or not. So we started basically trying to fit this scatter using various kinds of approach. One is with the mean, one is with the essentially the most probable fit, etc. But nevertheless, the most important outcome is that when you look at the auto power spectrum of the C2 signal, if you do not include the scatter, then essentially you are either underestimating your signal by more than 200% or sometimes 250% or so, depending on the scale. So, and depending on the model of the scatter that you implement. So, one should take into account this particular scatter. Next thing is, once you think about the scatter in the source model, how does that source model scatter affect the IGM signals? So, people have worked out a bit on this as well, and where they have actually looked into the ionization field's power spectrum and impact of the scatter on that ionization field power spectrum, and they kind of reported that there is no significant effect essentially. However, Kanan Datta here, he proposed maybe this scatter introduces some sort of non-Gaussianity, additional non-Gaussianity in the signal, and power spectrum is a two-point correlation function, would not be able to detect that non-Gaussianity. So maybe we should look at higher order statistics after including this particular scatter in our signal. So we did the same. We actually modeled included a log normal scatter in this line luminosity and halo mass relationship into our simulations and generated many realizations, essentially 300 such realizations, and looked at something called bispectrum. First of all, we looked at the power spectrum and we didn't see much of an effect. There is 10% or so effect at some scales, but not much, which is kind of in agreement with the previous work. Whereas when we looked at the bispectrum, essentially the effect was quite significant. But whether this effect was just by chance, just statistical fluctuation or not, to test that, we also did a statistical significance test where essentially we calculated the ensemble average of the sigma of that change, that's impact due to that scatter. And we set the criteria where the the statistical significance is more than 3 sigma, we will consider that as a significant effect. And it turns out that it affects the small scale bispectrum, that is large K mode bispectrum, where the statistical significance is high as well as the impact is also high. And this is simply because of the fact that in different realization, the small scale bubbles, actually small scale ionized regions vary from realization to realization. That's why this effect is significant at small scale, but not at large scale. Now, we also looked at a scenario where essentially we modeled this CO instead of C2, now CO, luminosity halo mass relationship, and we made this luminosity pretty low, extremely weak, so weak that it is not detectable using any of, let's say, the COMAP surveys at 3 sigma level, at least at certain parameters, for certain parameters of this model. But when we started looking at the cross power spectrum instead of auto power spectrum of CO, we started to pick up this extremely weak signal. So cross power spectrum actually helps you to pick up the extremely weak signal that is not detectable via the auto power spectrum. There are other reasons why you would do cross correlation, but this is one of them. Now, moving into the post-reionization era, essentially we ask the question, okay, what happens at this phase? So at this phase, essentially the 21 centimeter signal as well as your C2, CO and other line intensity maps will come from the same sources, the galaxies, right? So if I want to know how the matter has clustered on the basis of galaxy survey or on the basis of intensity map, what I will actually gain if I choose galaxy surveys. The problem with galaxy surveys again is that you miss out on the faint galaxies, so your interpretation will be extremely biased. On the other hand, if you choose these line intensity maps to do in post-EOR, probably you get a better constraint on your baryon bias essentially. So that's the question we try to address. However, what instrument you would do, and we chose SK simply because of the fact if you look at the documentation of SK in the phase 2, there is a proposition of adding a high frequency feed. So you can in principle observe both 21 centimeter and CO 10 transition line intensity maps using SK phase 2, SK mid essentially simultaneously in these overlapping redshifts. So there is a range of redshifts which kind of overlaps. So the first question is that whether these redshifts, at these redshifts things will be detectable or not, and this particular work is led by this particular student, Mohit, and so we essentially simulated again in the same fashion the 21 centimeter signal. Now the 21 centimeter signal comes from the galaxies and the CO signal from the galaxies as well, following the same formalism. But this case we used illustrious TNG simulation, so which actually gives you the H1 mass by default, and also you have the star formation rate density. So from the star formation rate density, then we painted the halos with CO luminosity. Now once you have simulated these two things, you then ask the question what statistics to use. So far I have talked about Fourier statistics, 2-point or 3-point correlation functions in Fourier domain. However, you miss out if you do those kind of statistics on the fact that the phase information is completely lost because it is some sort of an average that you get. So to obtain the phase information, you need to do some sort of morphological analysis. So if you can make these coarse gridded maps of the universe using these line intensity maps, probably you should first try at least the morphological analysis on those maps. So whether those maps are possible to make or not, to check that we actually calculated the SNR for the 21 centimeter as well as for the CO. Now for the 21 centimeter, the situation is pretty grim. You need at least 5,000 hours of observation to get a 1 sigma detection at around redshift 1.4 or so. However, for CO using SK2 mid, just for 100 hours of observation, you can actually get a significant amount of SNR, more than 3 definitely. So we chose this particular redshift which kind of overlaps between 21 centimeter and CO emissions using the same instrument. And we applied 2 different morphological statistics. One is basically percolation transition statistics, which is determined by something called largest cluster statistics. So this has been applied in Galaxy Redshift survey extensively. What you do essentially, you ask the question, if there is a galaxy or a bright cell and all the neighboring cells are around it, how quickly this bright cell gets connected to other bright cells in how many quick iterations. By quick iterations, I mean you paint all the neighboring cells of a bright cell as bright and then do this map and then ask the question, are they connected with each other? If not, you do another round of painting for all of the bright cells, because now you have more bright cells, and eventually after a number of iterations, all of your cells gets interconnected. That means the structure has percolated. So that is the percolation transition. You can quantify this by something called LCS, largest cluster statistics, which is essentially volume of the largest cluster at any given time, any given iteration in this case, divided by the total cluster volume. Now, and you can calculate also something called filling factor. Filling factor is nothing but how many cells are bright divided by the total number of cells in your survey volume. So if you plot it and you see this sudden transition in largest cluster statistics at a specific value of filling factor, that actually tells you that the structure has percolated. So how many iterations do you need to get this percolation? That's the question we asked, and it turns out that more or less, for whether it is galaxy density or 21 centimeter brightness temperature, they more or less percolate almost at the same filling factor, whereas the CO is a bit later. The percolation happens a bit later. So to verify whether this statistic is at all, the results are at all reasonable or not, we chose another statistics which is called local dimension, which actually tells you whether the cluster of points, whether they are line, sheet or clusters, the cluster of points that you are looking at, and by calculating the local dimension, nothing else. So this dimension D is 1 for line, D is 2 for a sheet, and D is 3 for a sphere or a cluster or node. So we applied this on our galaxy density maps, our 21 centimeter maps and CO maps, and as you can see, the galaxy density and 21 centimeter maps more or less show something between a sheet and a cluster. So from 2 to 3, something in between that. Whereas the CO shows more or less same thing, but there is something slightly more weightage towards the sheet-like structure. So to verify whether this is at all detectable in an actual observation with SK or not, we essentially simulated the SK-like noise and injected it in our 21 centimeter maps first, and first of all, if you don't do any kind of denoising, you don't get anything about this related to this particular statistics. So you have to do basically some sort of a smoothing of your images by to do some amount of denoising, and if you keep on increasing your smoothing radius, essentially you start eventually to pick up the same sort of structure in your probability density function of local dimension. Whereas and that can be done only for 5,000 hours of SK observation, which is unfeasible, I think. However, if you are looking at the CO, then only 1,000 hours of SK observation, and without any denoising, just by setting a 3 sigma threshold based on the sigma of your noise that you have in your observation, you can start recovering the actual true signal morphology. And so the question that remains is that why we see slightly different morphology in case of CO and in case of 21 centimeter, because probably because the star formation rate might have quenched preferentially at higher local dimension, and probably it peaks at sheet-like structure. So with this I will stop here, and probably CO will be detectable. If you use CO, you can probably do this morphological analysis using SK, but probably not with 21 centimeter. Yeah, I will stop here.
Thanks, Suman. Now we have time for a couple of questions.
So this light cone effect, is this coming because your voxels have a finite size? So
the voxels are small, but the when you are calculating any statistics, you are taking a chunk of your observation along the line of sight. So how much chunk you choose, depending on that the evolution, that much evolution you have.
so the size of voxel along the line of sight
Exactly.
is long enough so that things evolve.
Yeah.
So the velocities don't affect the peculiar velocities.
So peculiar velocities are already included in this analysis. So this is with redshift phase distortion. Yeah.
For the 21 centimeter cross correlation with C2, do
Yes.
you need to worry about extragalactic point source foreground in the 21 centimeter?
Yes, you do, because if you, in principle, the foreground for these two observations are different. One of the basically point of doing cross correlation is that because they are systematically different, if you cross correlate them, they might cancel out. But that is not completely true. It will impact your sigma, your variance of that particular estimator. So it is going to affect in some way. So some sort of point source removal is required. Otherwise, it will be problematic.
Is there a possibility of the point sources that are contributing 21 centimeter foreground or can also be contributing to C2 signal?
There might be a possibility, though the frequency difference, the frequencies that these two observing frequencies of these two lines will be vastly different, but there is a possibility that might affect.
Thank you.
Yeah.
So I have a naive question. This is related to assigning CO to a low luminosity objects.
Yes.
Because you are saying that intensity mapping is a powerful tool to look at the low density, low luminosity objects.
Yes.
That is true for H1, because H1 will follow at some level dark matter.
Right.
Whereas here there are two nonlinear effects. One is that metallicity depends on the luminosity or whatever you call mass. The second thing is that ISM fraction.
Exactly.
CNM fraction may be very low there.
Exactly.
So what will be the effect of actually including something like a chemical analysis in this? Because Simba and all, they do it, but they don't reach the kind of masses you would like to see in your distance.
I agree. So I think that particular part of the analysis is still unexplored, mostly. One of the major reasons is that obviously to do this chemical analysis at those low mass objects, first of all, you don't resolve them always, and even though you resolve them, then you don't have a large enough volume to make these kind of survey simulations, etc. So I think it depends obviously on the model, and it is something needs to be explored. It has not been explored properly. I don't think so. Yeah.
Hi, thanks for the nice talk. I have a question, naive question. For the CO signal, how well can we theoretically model the total intensity instead of the power spectrum?
Well, this is very naive model, whatever I have showed. So because it's just painting the luminosity of the CO based on the star formation rate in the
assuming this model, what will be the uncertainty in the intensity? There must be some theoretical predictions, right?
Right. So there are basically you can effectively play with these two parameters. I didn't discuss it at all, but yeah. So let's say there are these two parameters, this alpha and beta, which are again parameters of a scaling relation obtained from the local universe observations, individual galaxies. So we don't know well whether these relationships are at all valid at the high redshift or not. That also has not been verified. So it's pretty unexplored domain.
Thank you very much. Thanks.
Okay, so thanks, Suman. Our next speaker is Dr. Shomir Choudhury from IIT Madras, and he's going to talk about current status of cosmological 21 centimeter observations.
Okay.
Shomir.
Yeah. Okay, so I like to thank the organizer for giving me this opportunity to present our work. So they are my collaborators, so I will present on behalf of all of them. So in 21 centimeter observations, what we observe is basically the intergalactic medium, the neutral hydrogen is there, and there is a background sources CMB, and it's passing through the IgM, and we measure here the relative brightness temperature as compared with the CMB. That is the 21 centimeter fluctuations we want to measure, and it depends on that spin temperature and the radiation, basically the CMB. And based on the relative amplitude of these two, either it will be absorption or emissions. So how it looks like as a function of redshift from the initial stage. This is basically the absorption and at the later stage, basically the post reionization, the signal will be 0, and when the reionization begins, it will be emission. So depending on which redshift we are trying to measure, the amplitude will be either absorption or the emissions. And this is the neutral, completely neutral, and when the first source of as Suman mentioned, the first source appear, it will start ionizing the intergalactic medium, and we see this. But it is not the whole story, because we are not, when we start the observations, it is not like the 21 centimeter. Lot of other complications arise because of the foreground, our own galaxies, the synchrotron emissions and the system noise, which is much higher as compared to the, so somehow we have to remove them to get rid of the, go to that level of the sensitivity to measure the 21 centimeters. So that is the generally two approach people use to remove the foreground. What is the foreground removal? We assume that the foreground is much smoother as a function of frequency compared to the 21 centimeter signal. So what we do generally, we remove the smooth component from the observations, and what is the residual, that is we believe that we can remove. If there is spectral structure also, it will affect the signal, that will some leakage. Another thing is that foreground avoidance. Whatever the smooth frequency dependence, if we plot them as a function of perpendicular and parallel, that is the Fourier space, the smooth component will reside in this wedge-shaped region. So no need to remove, just avoid this part of the Fourier space. And we will concentrate, this is the UR window, we can concentrate only this part of that Fourier space. There will be some signal loss, there will be some sensitivity will be gone, but we can focus on this part of the K space to get rid of the foreground part. So that is the two methods generally people in the community use to get rid of the foreground part. But again, the noise will be much higher as compared to the signal. So instead of all the current observations are not that much sensitive to measure the 21 centimeters. So generally we use this power spectrum technique, that is the statistical quantity, to increase the sensitivity. So this is the 21 centimeter, we do the Fourier transform, and then we are measuring the fluctuations as a function of Fourier mode, and this is the power spectrum we are interested. So our aim is to measure the Fourier component, or basically the power spectrum, the amplitude of the Fourier component as a function of K, to measure the 21 centimeter power spectrum. So this is one of the sensitive telescope GMRT, and this is the 21 centimeter fluctuations. The radio interferometer, it measures the Fourier component, basically the Fourier transform of the brightness temperature fluctuations. And if we use this Fourier component measured at different Fourier modes, what we want is the 21 centimeter power spectrum. So that is the aim of this 21 centimeter observations. We have the fluctuations as a function of redshift at different part of the universe, and what we will measure as a radio interferometers, we have the Fourier component at the mode, and we have to remove the foregrounds, and finally we will measure the 21 centimeter power spectrum. So that is the whole story in the 21 centimeter we are trying to measure. How we measure that? Because the power spectrum is not the observable quantity is the visibility. So if we correlate the two visibility at two different frequency space, that is the delta nu separations, it will basically the Fourier conjugate of the power spectrum. So we can measure so visibility is the observed quantity, we measure at two different frequencies, and if we correlate two visibility at two different frequency separations, after doing the Fourier transform, we can measure the power spectrum. So that is the how it is related with the observable quantity and what we want to measure. So two visibility correlation formalism is the we will use for the power spectrum. So what is the current status of the 21 centimeter observation? This is the summary plot of all the recent upper limit of the 21 centimeter power spectrum. This is the GMRT here in the Presiga, it is 2013 upper limit, and all the other telescopes MW LOFA are there. So the most sensitive is now is the Hera one. Yeah, still it is few orders of magnitude in the magnitude higher than the expected signal. What SK will give us? The SK will have the enough sensitivity to measure the signal in the real space, not in the Fourier space that I have discussed in the power spectrum. So this is the simulated, and what SK will look like. We can measure the bubble, the ionized region using the SK, that is have enough sensitivity to measure the actual brightness temperature in the image domain. Now I will talk about our efforts that we have been doing for last several years in terms of the 21 centimeter observations. So again I said the foreground and the noise are the more challenges in the 21 centimeter observations. There is another challenge is basically called the wide field foreground. What is this? We have concentrated part of the sky, that is the field of view, but even we are concentrated a small part of the sky, but the residual the foreground, which is quite far away from the center of interest, will oscillate the signal. As I said, the foreground is the smooth component along the frequency, but depending on the instrumental response, basically the frequency dependence of that, it will create some oscillations. So that is the another challenges of the instrument, inherent to the instrument. We can't get rid of that. So that is the oscillatory pattern actually in the terms of the because of the instrument response. So somehow we have to remove this smooth the instrumental response to remove the foreground. So that is the wide field foreground we called. So this is the symmetric diagram. This is the primary beam response, and the signal, the foreground is quite far away from our center of location. But what happens because of the primary beam response, this feature will change as a function of the because of the primary beam response of the instrument. This will create the oscillations pattern in our frequency dependence. We can't remove this the oscillatory pattern using the normal smooth foreground technique. So that's why what we do here, we remove the sky response using some primary beam, some window functions, that is the tapering function with Gaussian functions, to remove the whatever the smooth component, whatever the contribution in the sky outside of the interstellar region, we want to remove them using some window functions. And as the visibility we measure in the Fourier domain, what we do generally the convert the measured quantity with the Fourier transform of this window function. So that is the technique we use, basically the tapering, to remove the frequency dependence of the primary beam outside of this the region that we are interested. So that is the tapering rapid guided estimator we have developed to measure the power spectrum. So that is just the mathematical technique. We remove the self correlations also, because the noise is dominated at the self correlations, and it is a highly basically computerly much faster compared to the normal estimator. It's also the side lobes that are basically the outside of the primary beam also remove the noise bias. So we have developed the estimator, and then we have applied this into the data, and that is the upgraded GMRT data we have used for the 20 centimeter measurement. So this is the UGMRT, now the upgraded GMRT. This is the band earlier as compared with the GMRT and UGMRT. This is now quite large bandwidth, and this is the antenna 30 antenna distributions, and this is the 45 diameter each. And as the function, as this telescope rotate, it will fill the whole UV domain. This is the one of the measurement of this galactic synchrotron, which is a large scale emission of using the GMRT, and we use some tapering basically just to observe the large scale mode, and basically this is coming from the fluctuations of the synchrotron emissions, and this is the power spectrum, the angular power spectrum of the synchrotron using the UGMRT observation at the band 2, basically the 150 megahertz, and at some L, up to some L, we can measure the angular power spectrum, and the power law is consistent with the synchrotron measurement, and the high L is basically dominated by the noise. So we can restrict this up to which we can measure the galactic synchrotron. So this is another measurement of the galactic synchrotron using the GMRT. This is slightly off galactic plane at 2 it's a plus minus 10 degree of the galactic latitude, and this is the measurement again using the angular power spectrum, and this two region basically this plus minus 10 degree, and we measure the angular power spectrum, and if the slope is consistent with the synchrotron emission. So we have measured the angular power spectrum. Later we have extended our observations to the TGSS survey, all sky GMRT survey at 150 megahertz. So you have used this TGSS survey, the publicly available data, and to measure the angular power spectrum at all over the sky. Basically this is the synchrotron, because the 21 centimeter is still quite it's quite low as compared to the synchrotron. So what we measure, we remove all the bright point sources from the data and measure the angular power spectrum from the left panel is before removing the bright point sources, because this is the mainly isotropic, the radio galaxy is distributed all over the sky. Right hand is basically after removing the extragalactic component. This is mainly the galactic component, the synchrotron, and there is a high intensity at the galactic plane, and these regions are basically the southern hemisphere, which is not able to we can't observe using the GMRT. This is another GMRT observations at 325 megahertz. This is the earlier one is at 150 megahertz. This is 325 megahertz, and we measured this is the image of the sky. This is the Elias N1 field, and we apply the TGE to estimate the angular power spectrum of the synchrotron, and this is the power law as a function of frequency. So there is some power law break at some frequency. Still we are investigating why. But we saw some break in the frequency as a function of frequency. It's not exactly same power law follows the whole range of the angular power spectrum of the synchrotron. So there is some power law break. We are not sure, but we are still investigating the issues. So this is the angular power spectrum. Now, as I said, if we correlate the frequency at two different frequency channels, the angular separations, we can measure the power spectrum after the Fourier transform. So basically, what the problem is that in the GMRT there are a lot. So basically, this is the white region is the flagged at the band 2. These are the only available region in as a function of this is the channel. So only the few persons are available at the band 2 observations for the GMRT because of the RFI and other issues. So if we do the Fourier transform using this type of flagging pattern, we will get this kind of nature, but the signal is here. Because of the flagging pattern, we will not able to measure the power spectrum at this, basically these are the K modes, because of and the signal is here. So somehow we have to remove the flagging pattern that is creating this kind of extra features. So what we do generally, we are measuring the Fourier transform, we are correlating the phase, so in this nature, basically we do so the power spectrum you can measure is both ways. Either do the Fourier transform first and then correlate. Later, either you can, or you can measure the frequency separation first and then do the Fourier transform. So this is the delta nu separations. In this way, you can just get rid of the flagging problem, and you can measure the power spectrum. So you see here, I first measuring the delta nu as a frequency separation measure. Even in the 90% data, 80% data are flagged, you can measure the power spectrum quite accurately. So this technique we have used for the 150 megahertz, and we see that this power spectrum in this region is basically the consistent with the noise. So again, we use the GMRT band 3 observations and we measure the power spectrum, but there are some issues we are facing, because when we remove the delta, so the next problem will arise because of this correlation of the ALL and RR. This is two different polarization. This signal will also pop up. So what we do is generate the cross correlation, two different polarization observation. If we cross correlate this RR and LL, it will give the more sense of the some correlated part will be get rid of. So that's why we use these cross correlations, and also we remove the some kind of foreground. The Asif will talk about all of this, and this is the final power spectrum from the GMRT band 3. We have removed the foreground using some polynomial fitting, and we have achieved this much power spectrum. So these different lines for the different techniques that I have discussed. So this is basically this is the Stokes I power spectrum, And if we cross correlate this RR and LL, we will get this kind of this power spectrum. But when we remove the foreground, we can go deeper level. So what we are trying, basically trying to improve our, based on your available data, we are trying to improve our technique, how far we can go toward this level. So we are facing, so we have removed we have removed some of the instrumental effect, then we show another effect. So this way we are just trying to improve our analysis technique so that we can go beyond it, so that we can go deeper and deeper upper limit. So recently we have started with this MWA also. So this all the results that I have showed for the GMRT band 2 and band 3. So we have started with the MWA data analysis also. This is a 256 element and this is the frequency range. This is the tiles, 4x4 tiles. And we have observed this part of the sky is basically the, this is the deep scan observations. This is the RA 0 to RA. So this is the total deep scan of the sky. We have observed this RA range 349 to 70 degree with different pointing centers. This is 162 different pointing center, one like this, and then this total region is covered. Total duration is 5 hours per night, 10 nights we have observed, and then this is the flagging pattern of the MWA. Because of the periodic flagging, it will create another this kind of ripple. So this we have removed using some smooth component filtering, and we have, so this periodic flagging is basically creating some horizontal pattern in the MWA power spectrum because of the instrumental response. This is basically the periodic flagging. So Asif will talk about more in the Tuesday, next Tuesday. So this is the power spectrum after removing this smooth component because of this, and then we can see that the power spectrum is much, we can remove. So this is before removing this basically this horizontal pattern, but if we remove this horizontal pattern using this filtering technique, we can go the power spectrum into deeper level. So then we can combine all those pointings one by one. This is for one single pointing. If we remove this, we have add all the component, all the pointings, incoherently average this, then we got all the power spectrum, we have combined all of them, and finally we reached here. So basically this is the first one, and after combining all of these, we can limit, we can go to the deeper level of the power spectrum. So 23 we have 23 pointing center in the sky we have combined, and this is the final upper limit we got from the MW observations. So Souvik is leading this work. So yeah, so the summary is that our main aim is to measure the 21 centimeter power spectrum from the low frequency observations. We have developed the estimator to measure the power spectrum, but there are a lot of other effects comes in because of the instrument primary beam response, flagging pattern, everything. So we are working to, we are developing the different, we are improving our technique to go to the deeper and deeper level, and we are applying to the real data. So the GMRT band 3, band 2, also we are working on the band 4, and also we have started working with the MWA to finally measure the power spectrum, but still we are quite far away from the signal, but we are working. Yeah, thank you.
For the GMRT part, the UV plane is like not completely covered, right?
Correct, yeah.
So what kind of mode coupling does it lead when you are estimating the power spectrum?
Yeah, so basically one of the problem we face because of this sparse UV distributions, there will be some normalization issue. We are doing the Fourier, basically the convolution in the Fourier plane and then measure the power spectrum. So that's why, because of the not completely filled, we saw using the validation technique, basically the simulations, we saw some normalization issues in the measured power spectrum. So we have used this improved normalization technique using some unit angular power spectrum. So we use simulations based technique to get rid of this sparse UV coverage.
Okay, thank you.
A very nice question. So there is a, so you showed a plot with a K perpendicular and K parallel.
Yeah.
So why is it the case that K parallel is always larger, the probe K parallel is larger than K perpendicular? So I saw that the K perpendicular runs till K till 1 or something like that.
This one?
Yes, yes. So why? I mean,
Okay.
not this one.
Okay.
I mean, there are other plots too, where it showed that K parallel. Yes. So maybe this one too. So the K parallel is always larger than K perpendicular. Why is that?
Okay. So basically, this K perpendicular is depend on the UV, the antenna separations. That is basically the how far the antennas are. That will decide the K perpendicular mode. It is related to the antenna separation between the two antennas. So if your antenna is quite far away, this length will increase. So based on the available antenna configuration of the MWA or the GMRT, this will restrict the basically the antenna separation will restrict this range. The K parallel range will be defined by the how the frequency resolutions of your observation. So these are coming from the telescope configurations. So the delta nu basically the frequency separation, how much the better resolution in the frequency direction you have, you can increase this range also. So this is totally coming from the telescope configurations. Maximum baseline, that is this one, and the frequency resolutions, that will set this one.
Okay, thanks.
Next speaker is Anirban Chakraborty from NCRA TIFR, and he's going to talk about probing fast galaxies with JWST.
I would like to thank the organizers for giving me an opportunity to present my work here, which is titled Probing the First Galaxies with JWST, a work that I am carrying out with my supervisor Tirthankar Roy Chaudhary. So essentially, a few years ago, with the launch of the James Webb Space Telescope, has ushered in a revolution in the field of extragalactic astronomy, enabling us to look deeper and further back in time, particularly during the first billion years of cosmic evolution since the Big Bang. And this has been accompanied by detections of a large number of galaxies at redshifts of greater than 10. And this entire endeavor has not been without its own share of surprises. The first set of surprise that came in when the early results were coming in was the fact that JWST had been detecting a large number density of very massive and UV bright galaxies at redshift greater than 10, which was in odds with the expectations from traditional galaxy formation models calibrated to pre-JWST results. Here is a plot of the luminosity function, essentially the abundance as a function of luminosity, and these are some spectroscopic constraints, lower limits from the surveys and the bunch of theoretical models, and you can see that bulk of them were below these limits. Only the ones which were calibrated after the early results came in are consistent. And there was a pretty huge body of work in order to understand these results, and they came in two flavors, cosmological and astrophysical in nature. And I will not go into the details of them, but whatever be your solution to this issue, there are also implications of those solutions that you would like to believe, particularly given the fact that there are concurrent large-scale effects from galaxies, particularly regarding the ionization of the intergalactic medium, since we believe that the galaxies and the radiation from them drove this process. So therefore, any constraints on the properties of galaxies would immediately translate to our understanding of the progress and the timing of reionization. And a second subtle factor that comes in is the fact that along with the radiation from galaxies contributing to ionization, they would also heat up the intergalactic medium, and this rise in temperature sets in a UV background that feedbacks onto the galactic processes, particularly star formation within low mass halos, suppressing their star formation rate and quenching them, thereby having a rich interplay between the process of galaxy formation and evolution with the progress of reionization. To leverage these things, we tried to build a self-consistently coupled analytical model, well, starting from the dark matter halo properties, and our goal was to estimate the statistical properties of galaxies and their large-scale impact. And this is usually framed in the language of finding a galaxy halo connection, which demands that we understand how to populate galaxies within dark matter halos, and we do this in an analytical setting. Which involves finding out the star formation rate associated with the halo in which that particular galaxy resides, and these involves modeling the star formation efficiency, the time scale, the availability of gas within that particular halo. And as I mentioned, that as reionization progresses, the availability of gas within galaxies which are formed in already ionized regions is expected to be impacted due to radiative feedback, and we account for that by this kind of a functional form which is centered around a critical mass scale which is affected by radiative feedback, and this only impacts galaxies which are forming in already ionized regions. And using this star formation rate, it is rather straightforward to compute the luminosity of the galaxy and also the ionizing emissivity from the galaxy, which involves modeling the intrinsic production rate in terms of the star formation rate, and using a light to mass ratio to get the UV luminosity, and also the fact that not all ionizing photons that are produced by a galaxy will leak into the intergalactic medium. And we solve this entire chain of things in a self-consistent manner to get handle on the observables. So essentially our approach involves modeling these processes, and we have 9 free parameters in our model that model the UV radiation production as a function of mass and redshift, the escape fraction of ionizing photons as a function of its mass, and a free parameter that takes into account the effects of radiative feedback towards the end of reionization, and we fit our model simultaneously to the luminosity function data and the reionization observables to get a handle on these parameters. So here I am showing the comparison with the data. These are UV luminosity function plots at 9 different redshifts from our model. And what we find from this exercise is the fact that the UV emission is required to be higher at high redshifts in order to match the JWST results. This is what these two plots show, basically the normalization and the power loss slope of this relation. And this can be interpreted through either having a larger efficiency of star formation, or star formation happening very quickly in bursty phases, or a different nature of stellar population altogether, which would keep the same star formation rate but give you a higher yield of UV luminosity. But the luminosity function is rather blunt in the sense that these appear in a degenerate combination, and it is very difficult to disentangle which is the primary reason behind them. Before moving on, we also check with the consistency with the reionization observables, and we find that our models prefer faint galaxy-driven reionization, where the low mass galaxies tend to show higher Lyman continuum escape fractions, which is quantified through these constraints. However, a check for the models or whether we have been able to pin down the galaxy halo connection using only luminosity functions requires us to move to higher order statistics, typically 2-point statistics like clustering, which is quantified through the galaxy bias. And we can do that in our model, since if we assume a particular model of the halo bias and knowing how galaxies populate halos. And here I am showing the respective predictions from our models for 2 different observation studies. We use the same cuts as done in those particular studies, and when we compare with the data, what we find is that these are the brighter galaxy samples, and we are able to reproduce their measurements without any further tuning of our model. However, for the fainter class of galaxies, what we find is that at low redshift we tend to overestimate the bias, and reconciling the bias measurements would require us to push these galaxies into low mass halos so that their galaxy bias predicted from a model is lower and in agreement with the measurement. However, there is a consequence into which we run into as soon as we try to do this, because low mass halos in our hierarchical structure formation are more abundant. So at these redshifts, if you try to push galaxies at fixed luminosity into low mass halos, you will end up overproducing their abundances. And this plot essentially shows that if you want to if you try to reproduce the galaxy bias and reionization observables, what we end up facing is a surplus of UV galaxies at these very redshifts where we are matching the galaxy bias measurements. And therefore, there seems to be a tension between the different data sets, and this is promising in the sense that these would enable us to pin down the galaxy halo connection much more precisely. To reconcile these different measurements under a unified framework, what we did is we took the resort of the concept of a duty cycle. Essentially what it means is that we assume that not all galaxies at a given redshift is observable to us in the UV. And our assumption that goes in is that only halos that have recently formed can host a UV detectable galaxy, and this definition of recently formation is one where we tie it to the star formation time scale. And using the duty cycle prescription of 20, we show here, we calculate the duty cycle, which is inherently mass dependent as well as redshift dependent. So here I am showing that the duty cycle for different values of our time interval increases towards massive halos at a fixed redshift, and also increases if you allow more time for fresh halos or mass to be assembled. And as a function of redshift, what we see is that this entire setup translates forward, because we expect halos to have higher assembly or assemble faster at high redshifts. And using this entire machinery, we proceed. This has already built-in characteristics of the fact that if you assume shorter star formation time scales, naturally the galaxies will be brighter. But since a smaller time scale means a smaller duty cycle, they would also not be, the probability of picking them up would be equally lower, representing this stochasticity of UV emission that is typical of high redshift galaxies. And the additional advantage of extending the model using a duty cycle framework is that we are able to break some of the degeneracies. And using this extended model, we redo the entire analysis of trying to match all those three set of observations under a single setup. These are the comparisons with the UV luminosity functions, and we are able to reasonably reproduce them. On the left, I'm showing the comparison with the reionization observables. We reproduce them and also continue to find that low mass galaxies are the dominant contributors. And on the right, I'm showing the comparisons with the galaxy bias, and particularly for the fainter galaxies, we are finding better agreement than our original model. Essentially, what this implies is, we find as a consequence is that that the star formation efficiency is needed to increase, as we already found from our only UV and LF analysis. But what we found new from including the clustering measurement is the fact that the star formation time scale requires a redshift evolution where it is low at high redshift, and representing the fact that the galaxies are more bursty at high redshift, and at a fixed redshift, galaxies hosted within low mass halos are more burstier than massive halos. But from this analysis, what we have also been able to find is break this degeneracy, and individually there are consequences or implications from the analysis. For example, the UV luminosity function has given us a constraint on this combined product, and as well as a handle on the star formation time scale. Here we quantify the evolution of the specific star formation rate as a function of redshift. If for two different galaxies, for example, one with -21, which is the brighter class of galaxies, and an intermediate class of galaxies, compared it with the bunch of individual measurements, and we are in reasonable agreement with the measurements here, although refined analysis would be required, since these points are not taken into account, these particular cuts. Secondly, what we can do is the fact that if we assume a value of a typical light to mass ratio, we are able to extract out the star formation efficiency needed, and that translates to predictions for the galaxy stellar mass function. And here we show predictions from our model and measurements from JWST data. And what we find is that we are able to reasonably reproduce the stellar mass function measurements available at present reasonably well from our framework. And therefore, to conclude, what I would like to emphasize is the fact that using a very simple analytical model that couples reionization and galaxy evolution, we have been able to explain a number of observables from JWST that has given us an insight into the astrophysical properties of these high redshift galaxies. And more importantly, what we have been able to demonstrate that including higher order statistics helps in breaking degeneracies in the galaxy halo connection that are remaining if we only use one-point statistics like the galaxy UV luminosity function. And with more data, probably our models will be put to stringent tests in the JWST era. Thank you.
No, I have a comment first and probably a question later. The comment is that it is nice that you thought about comparing stellar mass distribution with your prediction, but I simply warn you, because stellar mass is a derived quantity,
yes.
So that is derived under particular assumption of SFH,
yes.
star formation history.
Yes.
So I think you should be careful, otherwise you do the spectral slope versus luminosity. So that will be the better way of doing, because that is what is being used for the. Second point, this question is, you are using large scale bias. What is the scale at which this thing is computed?
So this is a ratio of the correlation function amplitude at 8 megaparsec H inverse by the sigma 8. So at those scales.
8 megaparsec.
Yeah.
Can some changes to the primordial spectrum or non-Gaussian entities help you resolve these issues? We thought of it.
Yeah, there have been, I think, some studies in the literature trying to address these issues. So I'm not entirely sure whether it will be able to solve the consistent, reproduce the consistent evolution of the UV luminosity function from 6 to up to 13. What studies have done is that they have usually focused only above 10 and not taken a wholesome analysis.
Yeah, so just quickly, just to clarify, so you find that you just how you resolve the clustering and the abundance issue is that you find that if you populate galaxies which have had a fast star formation in the recent history, then you can reduce the abundance.
Yes.
And also the clustering is correct, because you...
Essentially we use the duty cycle. The duty cycle is phrased in terms of how recent there has been an episode of mass change.
Right.
What we do is essentially push them to low masses, but kill the abundance using a duty cycle.
Using the
So,
duty cycle. And this comes out naturally from
Yes.
the accretion histories? Or
Yes,
you,
yes.
Okay. Or do you...
No, we use a model where the duty cycle is
sure.
quantified in these language.
In terms of that. The other question I had is, you also make predictions for low mass galaxies at, say, redshift 0, right? If I wanted to look at like, the satellites of Milky Way or something, and their...
We would not recommend that, because our analysis is restricted to redshifts above 6. So for example, probably this curve itself, if you pull down, maybe you will start seeing that there are issues. So.
Okay. But in principle, there's nothing...
Yeah, nothing stops us, but maybe retuning the analysis using some maybe AGN feedbacks will become relevant at solo redshifts.
Right, because there are reionization, say, quenching constraints from Milky Way satellites and stuff also.
Yeah, but we have not tried them at the moment. So our analysis is restricted above 5 or 6, roughly.
Hi, everyone. Thank you for the nice talk. I have a naive question. You showed many plots, so maybe I missed it. So there is also an upper limit on the UV luminosity between redshift 25 and 30. by some
Yeah.
photometric observations. Do
Yeah.
you
No, we have not used them
you have not,
because
that's
we
what
want.
pretty new, I think.
Yeah, yeah, we
Okay.
have not used them.
But in principle, your model should be, I mean, you can
Yeah, we
extend
can
it, right?
check whether we are consistent
With that upper limit.
with that upper limit or not.
Yeah, okay. Okay, thank you very much.
Yeah, so a couple of things. So did you consider reddening? You have not considered that?
No, we use an effective F star, which has a mass dependence. So implicitly, the behavior of reddening will be captured in the mass dependence of F star.
Mass dependent of F star.
Yes.
Okay. And you also mentioned the IMF variation that.
Yeah, we assume the traditional salpeter thing.
But you have not varied that.
No, because it is absolutely degenerate with this combination. So while we were trying to check this stellar mass function, we kept it as a free parameter, which will try to tune from salpeter to whatever IMF these people assume. So what Anand was saying. So this thing will be fixed that way. In the model, it's just one number that enters.
Okay, so thank you, Anirban. So our next speaker is Mohammad Kamran from INF OAT Trieste, and he's going to talk about observing Mach 21 centimeter power spectrum with SKA mid to explore post-reionization H1 distribution. 12 minutes plus.
Connect here. So first of all, I would like to thank organizers to give me a chance to present my work. So hi, I am Mohammad Kamran. So I am currently a postdoc at INF, and also I am collaborating with IFPU. So most of this work actually has been done during my first postdoc at Uppsala University. So my basically talk entitled basically proving the Mach power spectrum during the post-ionization era. So this is actually the artist impression of evolutionary history of our universe from Big Bang to present day. And as we know, universe from Big Bang to present day has passed through a number of phases like dark ages, cosmic dawn, epoch of ionization to present day. And we know that the two extreme phases which can be observed is basically cosmic microwave background and present day. Okay, so cosmic microwave background can be basically observed using, for example, Planck observations and Planck measurement, and present day can be observed using various galaxy redshift surveys. So we have well-known basically ideas of these two phases, but there are lots of missing pictures, and also these two phases basically provide clear picture of large-scale structure of our universe. So in these two extreme phases, we have lots of missing pictures of our universe, and most of them basically missing pictures lies in cosmic dawn, epoch of reionization, and post epoch of reionization. So Suman and Samir has already discussed about the CDEOR, and Suman has also discussed about something about post EOR. So I am not going into the detail. So today I will mostly focus on the post ionization era, which is basically the redshift below 6 and up to 0. So and we know that during the post EOR basically, so IgM is completely ionized and H1 is basically located inside the bound objects, for example galaxies or halos. So and we basically can observe the H1 21 centimeter signal from the bound objects, not from the IgM, because IgM is mostly ionized. So what is the 21 centimeter signal? Basically 21 centimeter signal is nothing but the spin flip transition of the electron proton system in the ground state of the hydrogen atom, and when there is a basically spin flip from parallel to anti-parallel spin, so there will be emission of wavelength of 21 centimeter or frequency 420 megahertz. So and this wavelength will be redshifted as per the redshift, and we will observe basically the early universe as per the redshift. So in this work basically I have used 3 different simulations.
So first I have used n-body simulations to populate basically the dark matter at different redshift. For example, 531 I have shown here, and basically in this dark matter distribution I have found halos using FOF halo finder algorithm, and then I used halo catalogs to paint those halo catalogs with H1 using very famous relation from Bagla et al. 2010. So this is basically empirical MH-MH1 relation, halo mass H1 mass relation. So here I have basically plotted on the top matter power spectrum and in the bottom H1 power spectrum. So here we can see that as we move from redshift 1 to 5, there is a basically increase in the power. Why? Because there is a clustering. So clustering is happening with the time. So power is also increasing with time. Okay, time is basically increasing, so power is increasing, or redshift is basically decreasing from high to low, power is increasing. But there is almost no evolution at various length scale in the H1 power spectrum, as we can see in the bottom panel. So why? Because first of all it will also depends on the MH-MH1 relation, because this MH-MH1 relation basically is kind of okay. If you basically increase halo mass, so H1 mass will increase, but after a certain threshold, for example 10 to the power 13 emson of halo mass, there will be no evolution in the H1, so H1 will be kind of constant. So halo mass is increasing after a certain halo mass, but H1 mass is not increasing. So here we have, and basically power spectrum mostly captures the high density regions, high density points, or basically over densities. So and here because the H1 content is kind of constant after a certain threshold in high halo mass, where basically the over density could be high. So H1 is showing almost no evolution over the posterior. For example, from redshift 5 to 1. So there is a kind of no evolution in H1. But of course we know that there are basically a number of small mass halos, intermediate mass halos, for example starting from 10 to the power 8 emson to 10 to the power 13 emson. Those halos exist, and inside those halos galaxies exist, and H1 reside inside the galaxies. So if halos are evolving, matters are evolving, so H1 could be evolving, right? But here we cannot see the H1 evolution in the H1 power spectrum, but there should be some evolution. So is there some method whether we can basically capture those evolution? So one answer could be lies in the terms of that, because H1 power spectrum, or basically standard power spectrum, mostly captures the Gaussian information, right? Or basically our information lies in basically in the Gaussian distribution, but there should be some non-Gaussian information in the distribution that is not captured by the H1 or basically standard power spectrum. But if we basically able to probe the non-linearity present in the distribution in some way, then there should be basically possibility of capturing the non-Gaussianity, and then through that connection in between non-linearity and non-Gaussianity could capture the evolution. Okay, so for this we have basically opted a relation which basically provide a relation between mark and density. So mark is nothing but is basically kind of transformation of the density distribution using this relation. So M is nothing but the basically distribution or basically kind of transformation of the density using this relation. So and this mark is basically defined as rho star plus 1 divided by rho star plus rho r to the power p. Okay, so if we just choose for example rho star 0 and p is 1, so mark would be just 1 by rho. Okay, so what does it mean? So if mark is just 1 by rho means if density is low, then mark would be high. Okay, so it will basically, in case of for example positive p, low density will be upweighted and high density will be downweighted. This is the one of the ways. If we choose for example negative p, so 1 by rho will be rho. So high density regions will be upweighted and low density regions will be downweighted. So what we are doing, we are basically kind of weighting our standard distribution using this mark developed by Martin White in 2016. and rho star here is the mark parameter, R is also resolution or basically smoothing length scale, and P is basically the exponent, okay, which will basically provide the amplitude of the mark, how basically how strongly we are kind of amplifying the basically upweighting or downweighting. So here you can see here the three different maps. In the left panel, basically I am showing here the standard density distribution, and in the middle panel I am showing the mark at P is equal to -2. So what it will basically provide with us. So it will basically upweight the high density regions. Here we can see that, and when we choose positive P, so here, so low density regions will be upweighted and high density regions will be downweighted. Okay, so this is the standard distribution. This is the mark distribution with negative P. High density regions are upweighted, and here low density regions are upweighted. Okay, yeah. So first I will basically show you the evolution of the mark power spectrum at two different smoothing scale. This is for 280 kiloparsec and 1.5 megaparsec, and I have chosen P positive, and which is 1. And we can choose rho star, for example, 0.1. This is basically one of the other mark parameter. So here we can see that with the positive P, low density regions are upweighted and high density regions are downweighted. And here basically we can clearly see the evolution of the H1 distribution, okay, at any of the smoothing length scale, right? And this evolution is directly reflected in the power spectrum, okay. So for example, when we are basically doing smoothing at 280 kiloparsec, here we are seeing basically a low power at low redshift, so power is kind of decreasing, and when we are considering R is equal to 1.54 megaparsec, which could be a characteristic length scale of the distribution, here we can see the power is kind of increasing. So basically summary is kind of there is some evolution in the H1 distribution which was not being probed by the standard power spectrum, but mark power spectrum can do, okay. And similarly, if we choose the negative P, so only the density regions, or basically which are already at high density, will be upweighted, and low density region will be downweighted. So again we can see the evolution in the power spectrum, right. So this means that both low density or intermediate density or high densities are evolving, okay, which is not being probed by the standard power spectrum. And also we have basically looked at how basically the mark power spectrum evolves with the smoothing radius. So we have considered here, let's say, smoothing radius from, let's say, 280 kiloparsec to 280 kiloparsec to 4 megaparsec, and here we clearly see there is an evolution in the mark power spectrum, for example with the positive P, okay, and here we have chosen the length scale K 0.16 MPC inverse, which basically probes the very large length scale. And also we can see here the evolution in the power spectrum, mark power spectrum at P is equal to -2, which probe the high density regions, right. So now we can basically summarize that here the H1 density power spectrum basically shows almost no evolution over the entire redshift range in the post TOR, but mark H1 power spectrum can show some evolution over the entire redshift range in the post TOR. So this is the summary of my talk. Thank you.
Thank you, Kamran. So there are several hand raised. So
Hi Kamran, actually in observations how will you do this marked statistics?
So this is actually a good question. So I was thinking in that direction. First we should need to basically kind of, so there could be two different ways. First we should basically need to make a map, okay, original map, or we can do and in the original map we can basically choose some threshold, okay, and threshold should be chosen in a way that whether with that threshold we can basically probe that observations or not, because if we choose very small threshold, then there should be possibility of basically not getting probed the mark power spectrum. So rho star will be an important, or if you are not making the map, which is also very difficult to make the maps, then we can basically kind of choose various number of thresholds starting from, let's say, a very small value to large value, and then we have to basically see what is the effect on the Mach power spectrum, and then we need to match it with the basically theory. So of course, with the observation it is difficult to do.
There's a small concern with the Mach power spectrum, and that shows up in your previous plot, which is you're essentially taking very small scale information
here
and pumping it up to larger scales.
Sorry, which plot? You are watching this plot?
So you see that it's very sensitive to your smoothing scale. The next slide.
Okay. Yes.
So modeling becomes extremely difficult.
Modeling of what?
Up to what k? So suppose you want the power spectrum at k equal to 1. The fact that you seem to see information in the Mach power spectrum is actually coming from much higher k. So unless you are extremely certain about your simulation, for example, the power that you're seeing at k equal to 1 may not be reliable. So have you thought
equal to
about
1
this?
would be very small length scales.
K equal to 1 is already small, but you see your smoothing scale, you had some 240.
No, length scale I have fixed here, 0.16 MPC inverse.
Yes, but the information you're seeing here is coming from much smaller scales.
Yes.
Through the Mach.
Yes. Okay. Yeah. So see, I am doing smoothing on a very basically large map. Okay. So this R is basically related to the characteristic scales. This R is related to the characteristic scales. Okay. So what is your actually characteristic scales of the distribution? But we are actually mapping the large scales because K is 0.16.
Yeah, Tirth has asked my question, but following up on that, how will you now, suppose you want to infer cosmology from your power spectrum, right? You showed that there's a d plus square dependence in the matter power spectrum, which is not so obvious in the H1 power spectrum because of the bias.
Yeah.
Now, if you put in your Mark, how will you disentangle, let's say, this growth factor from the Mark? In the context of observations.
Exactly. So I have no idea at this point because it's a completely first work, and we are basically kind of working on the other projects, and including the one that you are basically asking about, which is basically the bias. So yeah.
Small scale information comes up to large scale, so you can't really distinguish between linear growth and non-linear bias. So that's the problem with the Mach power spectrum.
It's for simulations. It's not very good for observation.
Not yet.
Until
we
understand this part.
Exactly.
Okay. So let's thank Kamran again.
Thank you.
The last speaker of this session is Rasi Jain, and she's going to talk about Alaknanda, a grand design spiral galaxy at z equal to 4 with JWST.
Yeah, 12 plus 3. Hi everyone, I'm Rashi Jain from NCRA TIFR, and I'm going to present my work, which is the discovery of a grand design spiral galaxy at the redshift of 4 with JWST. So at the time that it was discovered, it was holding the record of the highest redshift spiral ever discovered. But now there is another one at 5.2, and so in the background you can see a spiral galaxy imaged by Hubble and JWST. So here in the Hubble image we see that there are only stars and all the disk and everything, but here we can see all the dust lanes, and so that's how JWST is different. So now I will just talk about what was the case before the pre-GWST era. So earlier it was considered that these galaxies are rare in the universe, and most galaxies beyond the redshifts of 1 are either peculiar or spheroids. And galaxies are, at these epochs, galaxies are dynamically hot, so which tend to form clumpy structures rather than well-formed rotation dominated disks. And for density waves to emerge that can produce spiral arms, we need cold disks with low velocity dispersion, and they should be rotation dominated. And using HST data, only 2 spiral galaxies were discovered at a redshift of greater than 2. But now the number is increasing, but still it's not that high. So here we can see the comparison of JWST and HST filters. You can see these are JWST filters, and bluest one is around 9 micron. It goes all the way up to 4.4 micron, while this is HST ACS filter, and these are the one of the deepest filters of HST, and they go only from 0.4 micron to 0.8. There are some HST filters that probe this region, but these are much shallower than JWST, so these are not really useful. So, but why is JWST different? JWST provides us unprecedented resolution and sensitivity in near infrared, and because of this wavelength range, it allows us to find the optical rest frame at redshifts greater than 3, and only in the optical rest frame we can see the underlying disk of a galaxy and other features. In UV, with HST we can sample only UV, and where we only see the brightest stars like O and B type stars. So with many, after JWST has come, a huge number of disk population has been discovered at redshifts of greater than 3. Earlier it was supposed to be almost 0, but now it's known that these galaxies dominate the galaxy population at these high redshifts with around 60%, 40 to 60%, and hot disks are there, but cold disks are also available at these redshifts. So this galaxy was discovered in the uncovered data, which is in Able 2744 field, and it has full NIRCam coverage, and many medium band filters are also there. These are the broadband filters. So we have named it Alaknanda, because it's a spiral galaxy, and Milky Way is called Mandakini in Hindi, and Alaknanda is a sister river of Mandakini, which is tributary of Ganga. And so we identified this galaxy in a larger study of morphological properties of galaxies in the high redshift of 3 to 8, and out of that sample in uncovered data set. So uncovered data set has 70,000 objects, and in redshift greater than 3, this was the only galaxy that showed a very prominent spiral structure. There is also a candidate satellite galaxy here in this galaxy, and our photometric redshift is around 3.98, and the spectroscopic redshift is available for the candidate satellite galaxy, and that is 3.97, which is in agreement with our photometric redshift. So here these are 2.5 by 2.5 arcsecond cutouts made using JWST data. So these are the NIRCam shorter wavelength filters. Here we have used F090, F150, F200W as our blue, green and red channels, and these ones use 444W, 356W and 277W. So since these are the shorter wavelength filters, So we can see that the galaxy is kind of fragmented, and we see mainly the star forming regions. But when we go to the longer wavelength filters, like that I was talking about earlier, we are able to see the optical rest frame. We see the underlying disk, and so this galaxy is visible. And one more thing I want to add, this galaxy is not, it's almost invisible in the deepest HSD observations that are present at in this field. Here you can see different cutouts of these galaxies, and this red line indicates a 1 kiloparsec scale, and on the left I have written the rest frame wavelength in nanometer, which each filter is probing, and you can see that as we go towards the shorter wavelength filters, our galaxy becomes fragmented and it is almost invisible, which is why the HSD was not able to see it. And when we go to the longer wavelength filters, the arms are continuous, and there is one satellite galaxy also, which might be the reason of the formation of spiral arms in this galaxy. So for our analysis, we carried out stellar population synthesis using bagpipes, and we used the data in all the NIRCam and broadband filters, and we used data in one HST filter also. So this code basically generates model SEDs based on the given photometry and the priors that we give on input parameters such as stellar mass, redshift, and star formation rate. And after that, by Bayesian inference, it derives joint constraints on photometric redshifts and other stellar population synthesis parameter. We are using two types of star formation histories here. One is exponentially decaying SFR, and one is delayed exponential, which is more physically motivated, which means that star formation rises in the beginning, and at the later times it falls exponentially. This is a SED that here this orange curve shows the model, best fit model with bagpipes, and these blue points are our observed fluxes, and orange points are model fluxes that bagpipes has calculated. And we are also seeing interesting features such as this H alpha line, O3 line, and there is a Balmer break, there is a Lyman break, and this is all consistent with the redshift of this galaxy. So basically it's a large spiral galaxy with a diameter of 10 kiloparsecs. It's massive, it's highly star forming, and that is why it is similar to the spiral galaxies that are present in the local universe. And our photometric redshift posteriors are quite tight, which are constrained by observations in 21 bands. So this is another proof of our redshift. So this filter probes, this filter is able to see H alpha plus N2 line, initial line complex at this redshift. So these are the continuum subtracted images, and here we can see that the line emission is coming from throughout the disk, and this is also consistent with our redshift. We also carried out bulge plus disk decomposition morphological analysis of this galaxy, and we fit a Sersic profile to the bulge and exponential profile to the disk, and this is the residual that we find after subtracting the model. And you can clearly see that there are spiral arms, and its bulge to total ratio is also very small, which means that it is definitely a well developed disk at this redshift. So now we have to think about like what led to the formation of this galaxy. So there are two scenarios, cold disk scenario and hot disk scenario. So earlier it was believed that the cold disks are not present at these redshifts, but now they have been discovered up to the redshifts of 7 what can happen is that these cold disk, hot disks get fragmented, and then those clumps get dissolved over time, and then stable disks are there in which spiral arms can emerge via, for example, quasi-steady state density wave theory. And there is another hot disk scenario in which tidal interactions or bar interactions can also lead to the formation of spiral structure. And as I have told earlier, in this case we have a candidate satellite galaxy, so which might be responsible for the by tidally interacting and forming spiral arms in this galaxy. So this is the conclusion. So now in the contrary to the belief that was there, because by HST it is now clear that the disk population is there at high redshifts, and it is quite significant also. And we discovered a grand design spiral galaxy at redshift 4, and with 2 SPS codes, bagpipes and prospector being in excellent agreement for its photometric redshift. And now the question that we have is that what is the mechanism which is responsible for the origin of spiral structure in this galaxy. And for that we plan to put a proposal in the next cycle of JWST to get the net spec IFU observations of this galaxy, and we can also get the line map of this galaxy using ALMA using C2 line. Okay, so thank you.
Questions?
Hi, Rashid, thanks for a nice talk. A quick question on the distribution of the morphologies based on the masses of galaxies. Could you study any of these, like, because you said 60 or 40% excess, what are the mass distribution of the stellar mass distribution of these galaxies, depending upon their morphology?
Depending upon their morphology. Yeah, so actually in this redshift range, so in the local universe we have this situation that ellipticals are much more massive and everything. But at these times, these ellipticals and peculiar galaxies, they are just forming. But the disks are much more mature and evolved systems. So when you go to the larger mass side, there are actually disk galaxies that are more massive, but the other type of galaxies are smaller in mass.
Maybe we can discuss this a little later. Thank you.
Hi, Rashid. Sorry, thanks for the very nice talk. I have a very naive question. So you say you'll use this neat spec IFU observations. Can pipes and prospector be used for those spectral energy distributions? For those, do you know this?
IFU analysis cannot be done using bagpipes and prospector. So
Then you need another SED generator.
I'll need another code. I'll basically get the line maps, and based on that I can find out whether it's a rotation dominated galaxy or a velocity dispersion dominated galaxy. So that is the thing that I'm trying to prove using these observations, and this will help me to understand the mechanism of the origin of spiral structure in this galaxy.
Thank you very much. Thanks.
Any further question? If not, then let's thank the speaker again. That is the end of this session, and I will. Thanks. Okay. So now we'll break for lunch, and we'll come back at